to fill out to be cancer person, and the first page is just all the diseases that exist, and you have to check the ones you have. That's just to make you feel good. That you're like, oh, I only got like 1% of the diseases. I'm doing pretty good. And then the next page starts off, it says, have you, in the last couple of months, considered committing suicide? And I'm like, yeah, but only in the fun ways. And so I checked no. My wife's like, what does that joke mean? And I'm like, don't worry. It's not a problem. It's just like, I watched too much anime in high school. Just visualize cutting my arm off, but not in a fun way. And the next question on the list, it says, have you, in the last couple of months, wanted to go to sleep and not wake up? Oh! All right, the cancer paperwork has 2 suicide questions. They're like, yeah, you don't want to do that. But do you want to, like, what if we came at it from this way? And you're like, actually, I hadn't thought about that one yet. I super want to be alive for as long as possible, but now that you mention it, it has an appeal. Like, I want to go to sleep and not wake up for a while. If you're wondering why it sucks to wake up with cancer so much, I have a way of explaining it. Imagine the nightmare that we've all had, right? Where you've been hired by the mafia to kill the Baltimore Orioles. Like, all of them. The sports team, not the birds. That'd be fucked up, right? And you've done it. You did it. They were all at the sports game together. They were in the locker room, and you're just like, phew, all at once. But what you didn't account for is that there are a lot of retired Baltimore Orioles, and now they are very mad at you. And you are in an abandoned mall. And they can smell you. I don't know why. But you know. And so you duck into the Hot Topic. You get in there, and you get between the first aisle that you can find, and you're down on your knees just hiding in the aisle. But do you realize you've gone into the aisle with the jingly pants that they wear to the Insane Clown Posse concerts? And so you're trying to hide, but you also have to not jingle the pants. But the aisle is getting more and more narrow somehow. And the ceiling is getting lower, and now it's just like a tunnel of jingly pants, and you're trying very carefully, very seriously not to make any noise at all. But you can't help it. You bump a jingle, and it jingles, and you hear the Orioles outside stop moving and turn towards you. And I don't know if you know this, but a group of Baltimore Orioles is called a murder. And so you get down, and you're just like, they're coming, but I'm gonna hide as best I could. Like, maybe someone will save me. So you're laying down in the aisle with the jingly pants. And then, coming around the corner, you see a man, and he's got a catcher's mask on, and he's looking at you, and you're like, holy shit. And then you realize there's a gun in your ankle holster, because you're an assassin, and you pull it out. Oh, click, but it's out of bullets! And Cal Ripken Jr. pulls off his catcher's mask, looks down at you, and he says, strike 3, motherfucker. And the baseball bat rains on your face, and then you wake up, and you're like, holy shit, you guys, I've never killed anybody. I'm from Florida, so I've killed, like, fish and bugs. And crabs, which are like fish bugs. That's what happened. Aristotle said it's just a bug had sex with a fish. That's how we got crabs. So that's what it's like when you wake up and you have cancer. You're like, holy shit, I am both hunting and being hunted by the Baltimore Orioles. Except the Baltimore Orioles live inside your body and they eat you and you have to poison their food. So I go see my doctor about that. And he's like, so good news is Hodgkin lymphoma, great. It's one of the good ones. Now that we're staged and we know where you're at, you have a 5% chance of being dead. Just a 5% chance of being dead in 5 years. And I'm like, seems bad. I don't know. He's like, well, I see people with cancer all day, and like, I got one who's probably gonna make it. This is great. I love it. And I'm like, I see people doing TikTok dances inside of my phone all day, and they seem fine. Like, I'm like, doc, nobody does anything with a 5% chance of killing them, no matter how fun the thing is or how stupid the person is, unless they're a billionaire who wants to visit the Titanic. And, oh, I didn't know. Did something happen? Actually, interestingly, the summer I was sick, was a particularly bad year on Mount Everest. Like the death rate of trying to summit Mount Everest, like depending on the count, like approached the death rate of Hodgkin lymphoma. And I don't, if you've ever lost anyone in a mountaineering accident, I'm sorry about this, but I did find that to be like a source of comfort. And I'll explain to you why, because that's monster thought, but look, you got monster thoughts all the time, but especially when you're sick. But going up Mount Everest is like the hardest thing. That's why you do it, so you could say, I did the hardest thing. That's why I spent all that money and took all that danger so I could do the hardest thing. But it turns out it's like about as hard as having Hodgkin lymphoma, and I get to do that in bed watching Taskmaster. I did the math, it's actually cheaper to get cancer as long as you only do it for 1 year. And you have health insurance. And also, another perk, if you die of cancer, no one thinks you're an idiot. So, cool. This first appointment with my oncologist is a wild experience. It's so cool because he's not busy at all. It seems like he could talk for an infinite amount of time. Like, we talked for so long. Me and my wife were there, we talked for like an hour, and then he was still like volunteering questions we didn't even have to ask him. He was like, at the end, it was like an hour into the meeting, and he was like, a lot of people want to know, why did they get cancer? And I was like, well, Doc, I know why I got cancer. And he was like, oh no. Oh, which conspiracy theory am I about to hear from this man? I didn't think that he was one of those. Is it the chemtrails? Does he think it was the voting machines gave him cancer? And I'm like, no, doctor, sometimes ants have wings. And he's like, oh, extra no, I've not heard that one yet. Is that a lefty or a righty? Why can ants sometimes have wings, doctor? And he's like, I don't know. What are we talking about? Why are we talking about ants? And I'm like, it's weird, right? Like, if anything should be able to sometimes have wings, it should be giraffes. Not because they would work, but it would be cute. But no, ants get to sometimes have wings, and that's bad. They should be confined to surfaces. How can ants even grow wings? Wings are complicated structures. I don't get to sometimes have like the little Shrek horns that giraffes have, and those are very simple, just bones and skin. You know what I'm talking about? The knobs on a giraffe that control the volume and the temperature on a giraffe? But ants get to sometimes have wings. Why do ants even have wing genes, doctor? Do you know why, doctor? And he says, I don't know why. And I said, ants are descended from wasps. Yeah, bees too. Bees and ants are just wasps that decided to suck a little less. And so he's like, are you telling me that Ant-Man and Wasp is just like specialized ground wasp man and regular wasp? And I'm like, yeah, that's what I've been saying. And he's like, this is super cool. I was like, I wrote a letter to Marvel. And he said, what did they say? And I said, they said that I needed to stop writing them letters. Ants sometimes have wings, but the wild thing is they're not specialized for life in the ground. They're specialized for colonial life. And my doctor's like, colonial? Like churning butter in early America? And I'm like, no, living in colonies. See, ants are optimized for a weird way of getting their genetic information passed on. But here's the thing. They work together not to get their genes passed to the next generation of ant, but to get their genes passed to the next generation of ant colony. Doctor, I would like you to imagine for a moment that you are just a bunch of ants. And he's like, finally. Because look, for like basically half of the history of life on Earth, everything on Earth was single-celled organisms. They passed their genes on by just having one cell become two, and both of them had the same genes, roughly. But then, a bunch of different times, several cells would get together, and they would optimize not for that, not for getting their genes to the next generation of cell, but getting their genes passed to the next generation of colony of cells. And that's multicellular organisms. That's us. We are just a bunch of cells all working together in a marvelous little symphony that we totally take for granted, and we've only begun to really understand as a species, working together to do all of the wild and weird things that we do, trying to get us to correctly do the cha-cha slide at the wedding so that my wife will look at me and go, I guess. And then we can have a child. And he is now the new colony of cells that have some of my genetic information. That's wild. But here's an extra weird thing about ants. When they started becoming ants, when they were descending from wasps, that moment that happened, a single gene copied itself a bunch of times in ants with minor variations, and that gene was in the ability to smell stuff. Like, why do ants need all this ability to smell? Because that's how they control the colony. Ants don't know what they're doing, right? They just have this like remarkable set of pheromones for all kinds of different activities, and they smell each other, and it makes them do stuff. It's like high school. And so that's why they need all those ability to smell. They need ways to communicate, and our cells are the same way. Our cells are constantly communicating with all these chemical signals, like you can't cross this tissue boundary, here's where the blood vessels should go, all this stuff. It's amazing. But imagine, Doc, an ant who one day decides he's an individualist. He wants to be more like a wasp. His name is Trent. And Trent, because he has decided that instead of getting his genes passed on to the next generation of colony, he's just gonna pass it on to his clone. He's gonna clone himself, make a little extra Trent. And all of his descendants are the Trents. And the Trents can all signal the pheromones to tell the colony to take care of Trents at the expense of the rest of the colony. They're gonna have so many resources. The ants don't know what they're doing. They're just smelling stuff and it's making them do things. And so they start taking care of the Trents. And the more Trents there are, they're all gonna have this same trick to signal the ants to bring them food and take care of them. And so they're gonna have so many resources and they're gonna multiply exponentially until there's so many Trents that the colony can't support itself anymore and it collapses. And all of the ants die, including the Trents. Doc, that's what happened to me. One of my cells is a goddamn Trent. I got one cell that figured out how to confuse all the other cells into taking care of it at the expense of the rest of my body. And the weird thing is that this cell is basically a reversion to a single-celled lifestyle. This is a new organism that isn't me anymore, but its nearest ancestor is me. A single-celled organism whose nearest ancestor is me, and the only environment it knows is my body. And it loves it, and it's growing inside of it, and it has no idea that at the end of this process, it will go extinct along with me. And doctor, our job is to drive the Trents into extinction before they extinct themselves by killing me. And he's like, actually, I do have some other appointments I need to get to today. So how do we kill the Trents? First step, chemotherapy. And I go to get my first infusion at the infusion center. It's the nicest room in the hospital, big picture windows, it's got recliners. There's a nurse who's like assigned to you for the day. She's like, hello, I'll be your nurse today. We have cold yogurt and warm blankets and room temperature poison. One of those things is mandatory. Sit down, I get hooked up. She stabs me in the chemo port. They install a port in your body like you are a space station. And so she gives me the first chemotherapy bag, and she says, now, as soon as you're done with this one, you're gonna wanna try to pee as soon as you can, because they don't like this stuff hanging around inside of you. And I'm like, if you don't want it inside of me, why are you putting it inside of me? But once it's through the tissues and into your bladder, it's just gonna like be in there, irritating the lining of your bladder and making your dick hurt. So you just get it out as soon as you can. And then she says to me, and for the next few days, nothing that comes out of you should go into anyone else. And okay, we had just been talking about pee, me and this woman. And I like look around at all the like 80 and 90-year-olds in the infusion center, you know, people who got cancer and they're supposed to, and and I'm looking around and I'm like, this doesn't seem like a community that engages in like a ton of water sports. Like, she met my wife earlier, did she get a vibe? And she's looking at me, and I'm looking at her, and we're both waiting for the other one to break, right? I'm just like, you say it, I don't know what it is. And she's like, you'll get it, you taught me anatomy and physiology on YouTube. And I'm like, I don't know that I will. I don't see it. And so she's looking at, did I break first? And I swear to God, I say, like pee? Like pee? Like pee? like pee. Everybody in the room got it. I was doing a show and there was a 10-year-old in the front row. He got it. I just want to say to like all of the people in the world who made it necessary for my nurse to say that, like, wow, you're just like leave the chemo center with a little twinkle in your eye and you're like, let's go home, honey. I don't know what I'll shield you from my poisoned semen. I don't know, like it's this very strange. That's great that my nurse thought I might be a person like that. That's very kind of her, thoughtful to think that I might possibly do anything but just lay in bed and feel very sorry for myself. And so there's lots of bad parts of chemo. One of them is what we were talking about earlier, that like the white blood cell thing, so I'm like super susceptible to infection. So I'm basically on lockdown, shouldn't leave my house, but I have been told that I might die, so I feel like I need some very comfortable pants. So I go to a place called Shields, which is like, it's like a sporting goods store that's fuck the Chuck E. Cheese. And one thing you need to know about Shields is that if you let it, it would definitely vote for Trump. Like if you put it on a talk show and it was like a pundit, it would like sort of imply like subtly and lightly that my cancer was caused by the vaccine. That's the Shields vibe. But it's great, I love it there, except for that part. And so I was shopping for pants, but then I had to go pee my cancer out, and so I went into the bathroom and I was washing up, and there's a guy in there, and he looks at me, and he says, out loud with his own mouth, "Why are you wearing that?" And I was like, what the fuck am I wearing? Did I accidentally wear my Joe Biden is so cool shirt to Shields? Does it just like, gays? I was like, what am I? This is a weird thing to say to a person, and I realized I'm wearing a mask. Most people, I think, in this situation would be like, oh, God, now I'm dealing with this situation. Very upsetting. Why is this person acting like this? I hate this, and I'm very stressed out, but I am me. And so I had again, my brain tossed me this one. It said, this is gonna be the best part of cancer. Because like he was over here in Discourseville, and I was like inhabiting normal person land, and I was like, yeep. I can be in Discourseville. I do that all the time. And I hate it, and I shouldn't, but I do, and I know how. I was wearing a beanie, and I got to take my beanie off as the fastest way, right? And it's not like this, it wasn't like just bald, it was like in between bald, and like the 80 hairs that were still growing had grown out some. It was like a small wedding of hairs. And I pull off my beanie, and he's like, ooh. He sees it immediately, like my skin is the color of the ceiling. And he's like, oh gosh, and I got to watch him as he formed a memory. We all have these memories, right? These ones that we lay in bed and we think about, like the time that I told a girl she had a nosebleed, but it was a mole. And yeah, that was real, that's a real story. And here's the thing, he was super nice about it. And also, I was super nice. I knew that like if I was mean, it would be better for him. I knew that the nicer I was for him, the worse it would be. That's the only reason I was nice. I'm not a hero in this story. I wasn't trying to take the temperature down, it was just the best strategy for making it bad for him. And I knew that that night he would be staring in bed, like we'd both be in bed that night staring at the ceiling, not the same bed. I don't know, that'd be a weird way for the story to go. And then we kissed, and then we had to, but I did shield him from my poisoned semen. It's a beautiful story. We made it work. We healed America. And then I have to get radiation. That's the last step in my cancer journey. Lucky enough to be able to get radiation because it was in the right spot, basically, so I didn't have to do extra chemo. I could do radiation instead. And so I go get radiation, and my oncologist is like, there's a separate one for this. And she's like a nice, sweet little Southern woman. And she says to me, like, how are you feeling about the whole process? Like, are you comfortable? And I'm like, yeah, no, I'm into it. I unfortunately did, like, because I'm me, do the math, and I don't love what I discovered. And she's like, what do you mean? I was like, well, if you gave me all the radiation you're gonna give me in one day instead of like spaced out over a couple of weeks, I would die of radiation poisoning. And she's like, oh, honey, yeah, that's why we spread it out over 12 days. I'm like, no, I wanted you to tell me I did the math wrong. That's not what I wanted to hear. So you go to the place to get radiation. You go every day, and you walk in, and there's like, they call it the labyrinth, literally, that's what it's called. It's a room that is structured in such a way so the photons cannot escape and hurt people besides you. Labyrinths, not traditionally great for protagonists, but I'm in there. Lying down, and there is a particle accelerator in there with me, like most expensive machine I've ever been near. Gonna do like ridiculous things to my body. Like if I got this level of radiation exposure at work, I could sue them for so much money, but I'm doing it on purpose, so it costs money. And so I lay down on the thing, and it like sort of like moves around me, this giant robot particle accelerator laser thing, and then I know that it's gonna be like one of the most impactful things that ever happens to my body, and it happens, and it feels like nothing, and it makes this noise. Then it moves to a different spot, and it's like, it's the future. We have arrived in the future. Fucking make it sound cool. Like just, like now they make electric cars go like just make it like give it a space laser noise. So I do the radiation and then I'm officially cancer-free. Like that, it's weird. Being in remission is weird. I know that you want to cheer for me. That's good, you could do that. So, are there any cancers in the audience? Star sign, not disease. What's up, Cancers? What's up? This is the part of the show where we all apologize to you for having clearly the worst name possible for a star sign. Like the name to the star sign really reads like a list written by a person for whom the mushrooms are kicking in. Like in the beginning, they're like writing down the list. And he's like, can you put like lion on there? He's like, Leo, great, Leo, lion. Can you put scorpion? Scorpio, dope. That's also a cool animal. We're making a cool animal list. And he's like, bull, Taurus. I love that's great, cool animals. I love this cool animal list we're making. What's next? Fish. And he's like, well, fish is Pisces. That's like half of vertebrates. Guys, can you be a little more specific? Like, you can't just be fish. And he's like, no, fish. I want to put fish on the list. I don't know why. Okay, fish. What about human twins? That's weird. I guess that's also a couple of animals. What about a woman carrying water? Aquarius. Well, I've got an idea. Oh, this is cool. I'm seeing like, I'm gonna call it Capricorn, and it's gonna be a goat fish. She's like, we don't have goat on the list yet. We already have fish. We could just do goat. I wanna do goat fish. Goat fish. I wanna do Libra now. What's Libra mean? Scales. Like fish scales? You're doing a lot of fish stuff. No, like the device. I want to do the device scales. Like for weighing things? And Cancer, I want to put Cancer on the list. Belshazzar, are you all right? They're ancient Babylonians. So yeah, as a person who tells people stuff about how things are, I would like to tell the Cancers why their star sign is the same as the name for a bad disease. But I can't, because no one knows, and will never know. Obviously, both comes from crab, but why? So Hippocrates thought this up. Hippocrates, you might know him from the Hippocratic Oath. That's his most famous work. It goes like this. It's an oath that doctors take. It's really weird. I promise not to hurt people on purpose unless I have a good reason. And I'm like, okay, me too. Like, I like that, but I don't love that you had to take an oath about it. I read the Hippocratic Oath, the original one, because I was curious how it went down. And I will tell you the second bit is even weirder. Number 2, this is Hippocrates. He's like, number 1, don't hurt people unless you have good reason. Number 2, if you are doing house calls, do not seduce the slaves of your patients. Steve, like there's a guy for every rule, you know. Somebody's the reason that's in there. And number 3, do not, under any circumstances, treat kidney stones. Why? That seems like a good thing for a doctor to do. So I looked that up, and it turns out that in ancient Greece, there was like a whole class of professionals who just treated kidney stones, and Hippocrates was making this little doctor cult, and he didn't want to have a turf war over people's kidneys. And that seems very weird to us in the modern day, until you remember that we find ourselves in the same situation with regards to teeth. If you go into a normal doctor's office and you're like, I got a problem with my teeth, they're like, oh, why did you bring us in here? I took an oath. Do you want to start a war? You gotta go to the mall. And then the next one down is number 4. Is only 4 maybe, I don't know. Do not drink wine, only drink blood. I am vampire, very bad guy. That's why you can still do my accent. Number 6. 6, what a wonderful number. Ah, ha, ha. That's the Hippocratic Oath portion of the show. But I didn't tell you anything about cancer. So in a separate document he wrote down, and I will call this disease karkinos, which is Greek for crab, and then will later be translated to cancer, which is great because otherwise we'd be calling the rare form of brain crab. That would be not good. We don't want people to get prostate crab. And I will not tell you why, because 2,500 years from now, I want you fuckers to be arguing about it. An extra special fuck you to Hank Green, who will tweet about this, and then people will no, it's because the cancer, it grabs on like crab and won't let go. No, it's because the veins of the cancer are like the legs of the crab. No, these are interpretations from Galen, who is also old guy, but lived 500 years after me. Not all old guys lived at the same time. Hippocrates. P.S. Since we are having a good time, my name, Hippocrates, is 2 words. Hippo, which means horse, current hippo, just big fat horse, and krates, which means power. So my name is horsepower. Which in the future will be very cool. Vroom, vroom. But right now, it's just kind of cool. Power of 1 horse, clop, clop, clop. But that is all we have. Hippocrates out. So that, we don't know. We don't know why you're called cancer. It sucks you're either a disease or a bugfish, and that's what we know. But you did get the 69 as your little logo. That's dope. It's a nice little constellation prize. So, here's where I'm going to end the show. There's a lot of things that people say to people who have cancer, you know? I heard a lot of different things, and most of them are amazing and lovely. So you don't have to worry too much. But there's a thing that I heard a number of times that I want to warn you away from. It goes like this. How are you doing? And I say, I'm okay. And then they say, but how are you really doing? Do you want to come to my stand-up special? I can tell you how I'm really doing. What was your name again? Jolena, can I use your name? It's not in a nice way. You say that after the yes. Jolena, there's a 5% chance that I'm gonna be dead in 5 years, and a 0% chance I'm gonna tell you how I'm really doing. My mom is a Roman Stoic, and my dog is doing chores, and the flight attendant is crying, Jolena. I'm a bunch of ants. I'm like a bunch of ants, and one of my ants named Trent, and he's a real dickhole. Speaking of dickholes, my penis hurts. Jolena, is that what you wanted to know when you asked how am I really doing? You want to hear about the penis pain? Let me tell you about constipation. I thought it was a fun little thing that happens sometimes. No, the last step on the constipation journey is they cut you open and take it out. Jolena. You wanna know how close I am? I got close, but here's what it said in my symptom journal. Here's an exact quote. When it finally happened, it was like a 12-foot-long sisal rope with knots tied in it every 6 inches. Is that what you wanted to know? I'm a very private person, Jolena. But also, like, people are showing up for me in, like, big and little ways. Like, they're bringing me sandwiches and they're not making me go on the Zoom calls. It's really amazing to finally be in a place in my life where I feel like I can be the one who's getting support and not doing the supporting. And that was hard for me at first, but it took some adjustment, but now I'm doing it. And it feels really good. And it feels good to be a part of a community that, like, matters. And Jolena, this butterfly, look at that butterfly. It's beautiful and it's temporary. And it's part of the same 3.7 billion year long history of living chemistry that has been roving across this planet, finding life in every single crack and crevice in 3.7 billion years. That sounds like a long time, but it sounds like a longer time when you realize that that's almost 30% of the entire history of the universe. That's how long it took to go from one cell becoming two to like this, to all of you. It's like, Jolena, I'm jealous of cups. But also, I'm not a cup. Like, almost all of the universe can't think or see or feel or know anything. I get to be one of the tiny slices that gets to do that stuff, and that's absolutely wild. That's what I'm really doing, Jolena. And when you look at an ant colony, Jolena, the unit of the colony is the ant. And when you look at a person, the unit of the person is the cell. And the ants and people work the same way, where we use chemical signals to control how the colony behaves. But the unit of a humanity is a human, and we don't get to use chemical signals. We have some other way of doing it, and I don't understand what that is. And it's wild. It's wild that 8 billion people can live together on the same weird little rock and make it mostly work. But what are we signaling with? What's the thing that holds it together? Is it that this person loves this person who loves this person who loves this person all the way down the line forever? I'm thinking a lot about the Baltimore Orioles lately, Jolena. And either they're gonna get me or I'm gonna get them. But either way, what comes next, I think it's gonna be beautiful. Thank you, everybody. That was my shot. So, like any good stand-up comedy show, this one has corrections. The Titanic, if you go visit it, you actually have a lower death rate than just getting Hodgkin lymphoma. 250 people have visited the Titanic, and only 5 have died. Fuck. Cal Ripken Jr. is not a catcher, he's a shortstop. He was wearing a catcher's mask because that's scary. A murder of Orioles is not real. A group of Baltimore Orioles, not quite named, but someone has suggested to call it a pitch of Orioles, which is, I think, very clever. Ass crack hair may have a use. It provides resistance to the friction between your butt crack, and this can help for distance running. Matchbox 20 did not write closing time. I had to keep that in the show, though, because when I looked up Matchbox 20, I was like, well, I wonder where their name comes from. And I Googled it. The story is so boring. If you find out, it will make your life worse. But I also know that some of you, having been told this, are gonna go home and you're gonna go into Google and you're gonna type in Matchbox 20, name come from. And while your life gets worse, I want you to remember that I told you it was gonna make your life worse, but also I told you that because I knew you were gonna do what you are doing right now, and that makes me feel very powerful. Think about me.
If the trailer for this show opens with everyone booing as the word abuser is on screen,
Ever wondered just how fast you can push an Ender 3 before it falls apart? I want to find out too. My goal is simple. I'm taking my Ender 3 and and slapping on upgrade after upgrade after upgrade until its speed rivals the fastest printers out there. Today, we're going to go over what I've been working on over the past couple of months, and also talk about the things I still need to figure out. Let's start from the beginning. This was my Ender back in February. It had $100 worth of upgrades on it for my challenge with Tommy Houghton, but none of these mods were going to suffice. I took it all apart to start fresh. So what are the best upgrades for making an Ender 3 insanely fast? Well, looking at the printer, there are a few obvious ones. First and foremost, the y-axis. The heavy bed on the y-axis will always be a limiting factor for speeds and accelerations, and the stock V-wheels aren't very rigid either. If we want something to go faster, we have two options. We can either make it lighter, or add more power. So let's do both. Now, I want to make it clear that nothing I'm doing here is particularly novel. In fact, we've seen setups like this for quite a while on high-end printers like the LH Stinger. As you can see here, the Stinger has a bed made from a carbon fiber plate, which is super rigid and also extremely light. We can also see that the y-axis has two motors on it. An all-wheel drive setup like this has twice the power and half the effective belt length, both of which are beneficial for printing fast. I considered just stealing the LH Stinger's y-axis and putting it on my Ender, but I think I can up the ante even more. This is KevEnder, and it's currently the fastest 3D printer on the planet. Kevin designed some all-wheel drive motor mounts, as well as a handy bed mount that uses linear rails instead of V-wheels. The only downside to Kevin's setup is that it uses 6mm belts. Why is this an issue? Well, in short, wider belts are stronger and don't stretch as much under tension. And that's especially useful when you're trying to sling a heavy bed around with accelerations over 1 million millimeters per second squared. The LH Stinger that I mentioned earlier uses 9mm belts on Y, but I decided to go even further and try for 12mm belts on my build. I took Kevin's CAD and modified it so everything would fit. I also moved the idlers up so the belt path would be more in line with the rest of the bed, rather than pulling on the whole assembly from the very bottom. I really should have opted for live shaft idlers here, as normal toothed idlers limit me to around 15 pounds of belt tension before the bearings inside them start to die. Hopefully that'll be good enough. I printed out the motor mounts on my Q1 Pro and got to assembling them. For motors, I'm trying out the OMC 17HS192504S HV1 motors, or just OMC 2504s for short. These are relatively affordable, super high performance NEMA 17s that will get even faster once we add 48 volts into the equation, but we'll talk about that later. The main reason I chose them was because they have a 55mm long shaft. Without it, adding double shear support would be impossible for 12mm belts. I've also created some very large support feet for the y-axis extrusion, which will help stop it from tilting when the bed is moving. Again, these are not my idea. In fact, I was using LH's cross-support feet on my Ender before this, and I liked the design so much that I had to incorporate it into my new motor mounts as well. I'm not going to mount the support feet until everything else is together though, as currently they just kind of get in the way. For the bed itself, I opted to modify the existing Ender 3 bed and carriage. I made the carriage more symmetrical and carved out some extra space so it wouldn't collide with the stepper motors. The bed itself is basically the same as stock. I just made it slightly smaller for better compatibility. You can buy heaters for the LH Stinger on AliExpress, and I wanted my Ender to be able to use these as well. I got the carriage and the bed cut from carbon fiber by the sponsor of today's video, PCBWay. PCBWay does way more than just PCBs. Of course, they offer high-quality, affordable PCB manufacturing, but did you know that they also offer CNC machining, laser cutting, and even 3D printing? Whether you're just a hobbyist or prototyping your next big project, PCBWay has all the tools you need to bring your ideas to life. For today's video, I've used their CNC machining and laser cutting services, and the quality and turnaround time are seriously impressive. Check them out using my link below, and thanks again to PCBWay for supporting the channel. I was not expecting the carbon fiber to be so light. I'm going to weigh the two bed setups back to back and see just how much weight we shed. Starting with the stock bed and the glass print surface, it's looking like right around 1,300 grams all in. Pretty heavy. Of course, most people who do want to print fast won't be using a glass plate anyways, so let's take that off and measure again. Without the glass, the y-axis comes in at around 900 grams. which sounds like a lot, but isn't bad at all. That might actually be lighter than the y-axis on my Vorons. Now, let's measure the carbon fiber parts. Of course, we also need to consider the extra mass of the printed parts, but all in all, this new setup looks to be just under 450 grams. One thing to note, that 450 grams isn't considering the mass of the 2 MGN12 carriages that the bed attaches to, so it's probably more like 500 grams once you add those in. Still though, that's a huge improvement over stock, and I'm really pleased with the results. Now, let's actually get the y-axis installed. I printed some jigs to mount the MGN12 rails to the Y-extrusion, and I carefully tightened those down. It's going to take some careful adjustment to get everything running smoothly. The motor mounts slide on the front and back, with the motors and double shear support being installed first. The idlers at the top run on 5mm pins, and everything feels quite smooth. The carriage mounts install to the MGN12H carriages, and then the carbon fiber carriage screws into those with 6 heatset inserts. I'm using washers everywhere to hopefully stop the screws from coming loose. Realistically though, I'm going to need Loctite on all of these screws. One thing we didn't talk about just yet was belt attachment and belt tensioning. For that, I designed a little piece that sits between the carriage and the bed itself. One side clamps the belts into place, and on the other side we have a tensioning mechanism. With a long enough hex key, we should be able to tension the belts even when the bed is installed on top, and that's thanks to these access holes in the back. I'm quite proud of how this all turned out, but only time will tell if it actually works. Next up, we can move on to the X and Z axis. For Z, I decided to go with the OG Kevin aka Sam belted Z. This seems like the de facto standard for belted Z on an ender. I don't really have a lot to comment on here. I bought the pouch kit on AliExpress and it had all the required bearings, pulleys, and the rod, but do be aware that the kit doesn't come with hardware. I did need to mirror some of the parts in the slicer to get everything to fit properly, but that's just because I'm doing something special for my X-axis. You see, I wanted to go all-wheel drive on my X-axis as well, and I figured the easiest way to do this would be by simply replacing the idler on the right with a copy of the motor mount on the left. I got this piece laser cut and anodized by PCBWay, and I'm pleased to report it matches exactly with the stock piece. I had to install this plate using T-nuts since the stock holes didn't line up, but that's not an issue. For the X motors, I'm once again using OMC 2504s with a printed housing for double shear support. Unlike on Y, I'm not going to be using wider belts here, purely because I'd have to change the whole belt path for that to work. 6mm belts should be just fine here anyways. Now that we have the X-axis mostly assembled, we can put the whole thing together on the printer. Getting everything aligned here was pretty annoying, but it was worth it, because in the end I had a super simple all-wheel drive setup. One thing you've most likely noticed is that there's currently no way to tension the belts. That's a problem for future me when I'm working on the toolhead. Speaking of the toolhead, that's something I still haven't figured out just yet. I had good results with the dual overvolted 5015s on the budget build. In fact, those cooled so well that PLA parts would warp clean off the bed with anything over 30% fan speed. However, I'm concerned about reliability with a setup like that. There's also the mass of the fans to consider as well. For maximum performance, I'd like to try CPAP cooling, but to my knowledge at least, there aren't any existing Ender tool heads that support it. Between this and the belt tensioning, I will most likely need to make something completely custom. I have lots of time to think about what I want to do, since unfortunately I'm not going to be able to work on this Ender until September now. You see, I moved to a different province for the summer and I wasn't able to bring everything with me. As of today, I'm still working on getting my future YouTube studio assembled inside of this garage. But once that's done, I'll be back to videos as normal. This space is actually a lot larger than back home, and I'll be able to try some new projects that I wouldn't be able to do otherwise. Alright, I'm gonna leave it here for today, folks. If you have any ideas for upgrades I should install, or think I should have done some things differently, please don't hesitate to let me know in the comments section below. I'll see you guys in the next video.
Why are there crystals here, but not on this one? And how do solar panels even work? Let's find out. You can now buy a mug and a hoodie to help support the channel. Links down below. Solar panels convert light into electricity. They are photovoltaic, meaning light and voltage. It works with sunlight or artificial light. Take a small solar cell, set up your multimeter, connect the leads, and expose it to some light. We instantly see a voltage is generated. The stronger the light, the more electricity is produced. But can this be reversed? If we connect the solar cell to a power supply, it produces infrared light. The human eye can't see this, but if we take a camera and remove the filter, we can see that light is being produced from the cell. Light is basically just lots of particles called photons. The solar cell absorbs these photons. When they hit the solar cell, they knock another particle called an electron out of the solar cell, leaving a hole behind. This is the photovoltaic effect. I'll explain in detail how it works later in the video. But the hole drifts down to the bottom and the electron is pulled into the top layer. The electron is attracted to the hole, similar to how opposite ends of a magnet attract. If we provide a path using a wire, the electron will flow through this to get back to the hole. We place things such as LEDs in the path, and that way the electron has to flow through them, causing it to emit light, which means it emits photons. So if the LED emits photons and the solar cell absorbs photons, then can the LED power itself? Tell me your answers in the comment section and I'll tell you the answer later in the video. You have probably seen solar cells on your calculator or your garden lights. They're often used in motorhomes and boats. We see them on houses and even vast solar arrays in fields. An array is just multiple strings of solar modules connected together. A string is just multiple solar modules connected together. And a solar module is just multiple solar cells connected together. To make a basic solar cell, we start with a metal conductive plate. This forms the positive electrode. On top of this, we find a thin silicon layer. This is our semiconductor material. Typically, this consists of a layer of silicon-boron mixture on the bottom and a layer of silicon phosphorus on top. The joint between them is known as the p-n junction. On top of the silicon, we have an anti-reflective coating. A metal grid is then placed over this, which is our negative electrode. The thin strips are known as fingers, and the thicker strip is known as the bus bar. We typically have a glass protective layer over this because solar cells are very thin and they will easily break, so we need to protect them. This tiny cell has the bus bar at the very edge, this one through the middle, and these large ones have multiple bus bars through the middle. They all have fingers reaching out across the silicon to collect the free electrons. These electrons will flow along the fingers and then collect and flow together in the bus bars. We need as much light as possible to enter the silicon, and so the metal conductors need to be as thin as possible. More fingers make it easier to collect more electrons, but it also blocks light. The silicon material is shiny, which means light is reflected away, so the anti-reflection coating helps reduce this, but some will always be reflected. We also find cells with this rough surface. This helps capture some of the reflected light and direct it back into the solar cell. Each of these cells generates just 0.5 volts, but the larger the cell, the more current it can generate. To make a solar module, we have a solid back sheet with a layer of EVA adhesive over this. Then the solar cells are stuck to this and connected together. Another layer of EVA film sits on top of this, then a layer of glass, and finally the frame is fitted. On the back we have the electrical connections which connect to the cells. The EVA encapsulates the solar cells, insulating them from moisture and mechanical stresses which would degrade the material over time. Looking at the solar modules, the top of one cell is connected to the bottom of the next cell, and this increases the voltage. Looking inside this unit, we have two cells, both producing 0.5 volts. If we look closely, we can see the cells overlap and join to form a series connection. The ends pass through the back where we find the electrical terminals. Small modules use 36 cells, which produces around 18 to 19.8 volts, perfect for charging a 12-volt battery because we need more voltage than the battery to charge it. So we often find these used for off-grid systems. But most residential installations are grid connected and they use 60 or 72 cell modules. Commercial installations typically use 60, 72 or 96 cell modules. Some can be even larger. When we connect cells in series, the voltage adds together, but the current remains the same. This module uses 60 cells, each providing around 0.5 volts and 8 amps of current. So it produces around 30 volts and 8 amps. This gives us 240 watts of power. If we connected 4 of these modules in series, we would get 120 volts and 8 amps. The voltage adds together, but the current remains the same. This gives us 960 watts. But if we connected 4 in parallel, we get 30 volts and 32 amps. The voltage is the same, but the current adds together. This also gives us 960 watts. We often use a combination of series parallel connections. The modules connect to a charge controller and inverter. These have a maximum and a minimum voltage and current to work. For example, this one might be 100 to 150 volts and 25 amps. Our string of modules has 120 volts and 8 amps. So we can't add another string in series because we will exceed the voltage limit. Therefore, we connect 2 strings in parallel, giving us 120 volts with 16 amps. The system could be standalone or grid connected. We can use a solar panel to directly power a load, but it only works when exposed to light. For example, this solar fan will automatically turn on when exposed to light. The brighter the light, the faster it spins. But it doesn't work at night. We therefore need a battery to store the energy. It charges during the day, and we can then use it at night. That's how this very simple battery charger works. However, the voltage and current will vary, and the solar module can overcharge the battery, which will damage it. And at nighttime, the battery can discharge back through the solar panel. So, we separate them using a charge controller. Now, when the sun shines, the controller charges the battery. We can switch the light on, and the controller sends power to the load, with any excess energy going to charge the battery. At nighttime, the controller protects the solar panel from the battery, but it still allows us to use the energy stored in the battery. And that is how these solar-powered phone chargers work. You can see from this simple garden light that inside we have just a solar cell connected to a basic charge controller. This separates the battery and the LED. The solar cell charges the battery, and when charging stops, the light is powered. We can also control the light with the switch. The solar panel and the battery provide DC electricity. If we connect this multimeter to a battery, we see a constant flatline voltage. That's because the electrons are flowing in one direction, much like the flow of water down a river. We can use this to power small DC motors, lights, and USB devices, perfect for motorhomes and boats. But many of our appliances require AC electricity, which works differently. If I connect to this power socket, we have a wave pattern. The electrons are flowing backwards and forwards. It is alternating direction, much like the tide of the sea, flowing in and out. To power these devices, we need an inverter. This will convert the DC into AC. Inside, we basically just have some electronic switches which turn on and off extremely fast to control the path of the electrons. You can watch our detailed inverter video to learn more. But using an inverter allows us to use both AC and DC devices from this system. However, the battery will run out of energy if it isn't recharged. For domestic and commercial installations, we therefore often connect to the electrical grid. In a simple system, we have just the solar panels connected to an inverter. This feeds the breaker panel and the AC loads in the property. The electrical grid connects via a meter to the panel also. The inverter must therefore synchronize with the grid. At nighttime, no solar energy is generated, so we buy electricity from the grid. On a sunny day, the solar panels will be enough to power a few items.
Here's how to quickly connect up a DHT11 or DHT22 temperature and humidity sensor to an ESP8266 microcontroller. First of all, I'll recommend buying the DHT22 over the DHT11. They're said to be more accurate and also more robust. This cheap DHT11 I bought from AliExpress no longer works. Here's a chart that compares the two different types. A DHT22 is roughly twice the cost of a DHT11. Be sure to buy decent components that have good reviews. If you want more accurate data, then go for the DHT22. However, it's slower at taking measurements. Now let's get the sensor connected to the ESP8266 and take some temperature and humidity readings. So here's how to wire up the ESP8266 to
systems within the home, and so no electricity will pass through the electrical meter. On very sunny days, the panels provide more energy than we can use within the home, so the excess is sold back to the grid. This is net metering. More advanced systems will use a battery bank, which requires a charge controller. The solar modules will charge the batteries and power the appliances, but when the batteries are full, the excess power is sold back to the grid. At night time, the batteries power the home until they are empty. At this point, electricity needs to be purchased from the grid. In the event of a power cut, the batteries will power the home until they are empty, and then in the daytime they will recharge. Solar farms will have multiple rows of solar panels generating much higher voltages. These will then combine and connect into a large inverter and then feed into a transformer substation. Here the voltage is increased and it is then exported to the grid. The problem with solar is that the sun keeps moving. It moves from east to west every single day, and in the summer it's high in the sky, but in the winter it's low in the sky, assuming you're in the northern hemisphere. Solar panels work best when perpendicular to the sun. We can see with this torch that the light is strongest here, but as it tilts, the light is spread over a larger area, so it is less intense. Ideally, we would just move the solar panels with the sun, but this is difficult and expensive to do. So we need to assess the location for the altitude and the azimuth of the sun at that latitude. Then we have to check for shading, and then we choose the best orientation and tilt angle for the module. This involves a lot of data tables and maths, which is very time consuming. But with PVCase, our sponsor, you can simulate the actual location using their next generation AutoCAD-based PV software, which incorporates 3D topographical data points so you can prototype the design as well as the electrical cabling route and cable trays, and assess the placement of the inverter. The stringing and cabling can be automated or manually designed. And with their shade analysis, you can find and remove overshadowed modules to ensure optimal sun exposure design, and even compare different designs side by side. Of course, you can then export the projects. You can design ground and commercial or industrial roof-mounted projects, and automatically produce construction documentation as well as a bill of materials. This helps you save time from the initial design all the way through to the procurement phase. Perfect for large commercial, industrial, or even utility scale projects. Click the link in the video description to learn more. Do check them out. You might have noticed that solar cells look different. There are crystalline types and thin film types. Where have you seen them used? Let me know in the comment section down below. One of the most common is the polycrystalline cell. It typically has these blue flakes, although we can get other colors like this emerald version. These flakes are individual silicon crystals, poly meaning many and crystalline meaning crystals. They look beautiful, but each crystal is a separate group of atoms in different orientations. The boundaries of the crystals are defects, and they actually reduce the efficiency of the cell. These are very common for hobby electronics, solar-powered products, and also in solar panels. They are relatively cheap, but have an efficiency of around 13 to 17%. To make them, we basically take some silica sand and some carbon, such as coal, and melt it in an electric arc furnace. It cools down and forms these large chunks of raw silicon. This is a piece of raw silicon in my hand. It's very lightweight, and you can see it's very shiny. I'll leave a link in the video description for where to buy some. These chunks are crushed into a powder. They are mixed with hydrogen chloride and boiled into a gas. The gas is then distilled to remove the impurities, and it then enters a reactor and slowly collects on the surface of rods, forming pure silicon. The pure silicon rods are then broken up. They are melted and then cooled to form ingot blocks. as the material cools, the atoms join and form crystals. The blocks are then cut up into thin sheets and used as solar cells. This is a monocrystalline cell. It is rigid and it typically has a black or very dark blue color with no visible crystals. Mono means one. The atoms form a very orderly structure. Monocrystalline is more efficient, around 15 to 19%, but it's also more expensive to produce as it is more refined. The pure silicon chunks are placed into a crucible and melted. A seed crystal is lowered into this, and the silicon atoms start to stick to it. This is then slowly extracted, and as it cools, it forms an ingot. The atoms structure themselves perfectly in this process, forming one giant crystal. The ingot is then cut into blocks and then into thin slices to form the solar cells. We can also get thin film types. This monocrystalline version is flexible, and so is this polycrystalline version. These are often used for curved roofs of vans and boats. It has a shorter lifespan and is less efficient. This garden light and this calculator use thin film amorphous silicon, which has this brown color. The atoms have a random structure with no defined pattern. They are very cheap to produce, but only around 5 to 8% efficient. When we talk about efficiency, we mean the energy from the sun and how much is converted into electricity. The energy travels in waves. The waves are different sizes, from tiny but high-energy gamma rays to large low-energy radio waves. But most of its emitted energy is in the ultraviolet, visible, and infrared region. The visible spectrum is what the human eye can see. The wavelength determines what color light the eye will see. If we measure the energy per area by wavelength in space, we see a curve like this, but down at sea level, it looks more like this. And that's because the atmosphere has absorbed and also deflected some of the energy. Remember, inside the solar cell, we need a photon to knock an electron off of its silicon atom. We use silicon because the electron in the outer valence band only needs to receive around 1.1 electron volts to make the jump to the conduction band and then become free from the atom. That is equal to a photon with a wavelength of around 1127 nanometers, which is here on the spectrum. Any wavelength beyond this, therefore, can't be used to generate electricity with this material. But all the wavelengths below this can be used. However, the wavelengths have more energy than is needed, and so this excess energy is going to be wasted by heating the solar cells. And so there is only around 30% left that can actually be used to generate electricity with silicon. Some of this energy will be reflected away. Dust and dirt on the solar panel will also block some energy. And additionally, as solar cells heat up from the wasted energy, their efficiency will decrease. And after we've generated all that energy, we then also have energy losses from the inverter and also the wires. So this red LED cannot power itself. It has a wavelength of around 705 nanometers, providing 1.75 electron volts. We only need 1.1, and so the rest of this energy will be wasted as heat. But to produce the light, we are consuming 4 milliwatts, and only around 10% of that is going to be converted back into electricity. So we would need around 10 LEDs to power just one LED. I have tried it here, and 9 LEDs is just enough to produce light. LEDs also use silicon, and so do diodes. A solar cell is basically just a giant flat LED working in reverse. We can actually shine light into an LED, and it will produce a voltage. Check out our LED video to learn how they work in detail. When we look at silicon atoms, they have 14 electrons, with 4 in its outermost shell, known as the valence shell. Silicon atoms are most stable when they have 8 electrons in their valence shell, but they only have 4, and so they will share an electron with each of their neighbors to achieve this. So where do the free electrons and the holes come from? For the electrons, we add some phosphorus to one side, because it has 5 electrons in the outermost shell. 4 of these will be shared, and there is now 1 spare electron which is free to move around the material. For the holes, we add some boron to the other side because it has just 3 electrons in its outermost shell. There isn't enough electrons to share, and so there will now be a hole where an electron can occupy. So we now have a layer with too many electrons and also a layer with not enough electrons. This joins to form the p-n junction. N stands for negative because the electrons are negatively charged, and P stands for positive because the holes are therefore considered positively charged. At this junction, we get a depletion region. Some of the electrons move across and some of the holes also move across. But this will form a barrier with a slightly positively charged region and a slightly negatively charged region. This creates an electric field, which prevents more electrons or holes from moving across. And that is what forms the depletion region, where no free electrons or holes can exist. When light shines on the solar cell, the photons penetrate through the thin N-type layer and reach the p-n junction. If the photon has enough energy, it can knock an electron off of an atom in this region, setting it free and leaving an electron hole behind. Remember, no free electrons or holes can exist in this depletion region. So, the electric field pulls the free electron up into the n-type layer. The atoms share electrons, so another will move from the p-type layer to fill this hole. But this just leaves another hole behind it. This is also quickly filled, and so the hole drifts down through the p-type layer. A large amount of electrons and holes will build up in the two materials at their terminals. This causes a buildup of positive and negative charge, and this is what creates the voltage. The free electrons are attracted to the electron holes. Think of them like opposite ends of a magnet being attracted together. So if we provide a path, the electrons will then flow through the wire to get to the other side of the solar cell where it can recombine with a hole. The light hitting the solar cell will cause a vast amount of electrons to break free. These all flow through the wire and a current develops. As soon as light hits the solar cell, electrons will flow continuously. We have therefore generated DC electricity, and that is how a solar cell works. Check out these videos to learn more about engineering, and I'll catch you there for the next lesson. Don't forget to follow us on TikTok, Facebook, Instagram, LinkedIn, and of course, theengineeringmindset.com.
Thank you to Brilliant for supporting PBS. Physics is this close to understanding the entire universe. But what lives in this gap? Many physicists think that it's the elusive graviton, the quantum particle of gravity, whose discovery will finally allow us to stitch together our two great theories of nature into a single master theory. But what is the graviton? And does it even exist? We have a couple of important announcements before we get started. First of all, it's time for the PBS annual survey. We're looking for your feedback. Every year, PBS conducts an audience survey to gauge our audience's interests, vote on show ideas, and help shape the future of PBS. We really do look closely at the data, and it's incredibly helpful. Also, the Spacetime fans have been one of the most well-represented fandoms on the survey, and we'd like to keep it that way. We put the link in the description, and if you have a couple of minutes, we'd love to hear from you. Next up, we're still battling the algorithm, and by liking and commenting on the episode, you help get the episode shared with more members of the Spacetime community. It really does help. You can also subscribe and hit the bell icon to get notifications. Lastly, if you want to believe in a future with warp drives, you can head over to the merch store to get an I Want to Believe UV Glow t-shirt or sweatshirt. The quantum revolution started when we realized that light is made of particles, photons. Max Planck guessed it and Albert Einstein proved it. Light is a wave in the electromagnetic field, so even from the beginning of modern physics, we have this idea that a force, the electromagnetic force, is communicated by these particles. As quantum mechanics evolved into quantum field theory, we also found the particles for the weak and the strong forces. That's 3 out of the 4 fundamental forces, leaving only gravity lacking a mediating particle. So if we could just figure out the graviton, we'd have united all of the forces of nature and be on track to a theory of everything. We are now 100 years after the birth of quantum mechanics, and much of the past century of work towards the master theory hinges on the existence of the graviton. But does it exist? If not, much of the work in unifying these theories has been in the wrong direction. Now, we can describe the entire universe in terms of quantum mechanics and general relativity, yet they look wildly different to each other. On the quantum side, we have these fields filling all of space, whose oscillations give us the known particles of matter and 3 of the 4 fundamental forces. These quantum fields fracture into discrete shards as we zoom in, and their properties and their particles can never be pinned down precisely. But on the relativity side, we have space and time merging into a unified fabric of space-time, a fabric that can expand and warp. It stretches in response to matter and energy, leading to what we experience as the force of gravity. It's a pretty effective picture. Quantum theory gives us the stuff of the universe, relativity gives us the container. Matter in spacetime. Matter tells spacetime how to curve, and spacetime tells matter how to move. So if this picture works so well in describing the universe, why do we need to try to force gravity to work the same way as the quantum forces? Well, partially because the two theories are so different. We expect, or at least hope, that all of the complexity that we observe in the universe emerges from unified underlying laws. That proved to be true of all of matter and most of the forces of nature, quantum fields all the way down. It would be weird if the most fundamental layer of reality was actually two unrelated things, and extra weird if the theories describing those things are profoundly different, as they are in the case of quantum mechanics and general relativity. The former is fundamentally discrete and random, but the latter is fundamentally continuous and deterministic. But maybe that's just how it is, two separate theories. It's not very elegant, but does the universe care what we find pretty? Now there's another reason, besides aesthetics, that we need quantum theory and relativity theory to connect. It's because at a fundamental level they actively contradict each other. Together they describe most of the universe, but in certain places like the center of a black hole or at the instant of the Big Bang, they generate contradictions and paradoxes that, it seems, can only be solved by finding the master theory in which quantum mechanics and general relativity connect seamlessly. For various reasons, most physicists trying to solve this problem follow a particular path, the path of particles. They try to quantize gravity, just as they once managed to quantize electromagnetism. And the search for this theory of quantum gravity implies a particle that mediates gravity. That's the graviton. If the graviton exists, then gravity has to be quantum, and vice versa. Let's see why that's the case. So to get a photon, we start with the classical electromagnetic field, the one described by Maxwell's equations. A field in this sense is just something that extends through space and has some value at each point in space. That value can be a simple number, like say the density or temperature of the air in the room, giving us a density or temperature field. Or it can be a vector, a number and a direction. The EM field is like that, a strength of the force and a direction at every point in space. Fields can support waves, oscillations in the field strength that move through space. The density field in air supports sound waves. The EM field supports EM waves, which we know of as light. So when Planck and Einstein showed that light is made of indivisible particles, we were set on the path to quantizing the EM field itself. This process of quantization followed the development of quantum mechanics in the mid-20s and quantum field theory in the following couple of decades. Through quantization, the EM field is broken down into countless modes of all different frequencies. In this new description, even the empty or vacuum state of the EM field is made of those modes, made of infinite electromagnetic waves stacked and cancelling into nothing. And those virtual modes are made of discrete packets, just as is the real EM wave made of photons. So we can say that the EM field is made of virtual photons. In quantum field theory, we describe the quantum electromagnetic force in terms of other charged particles exchanging these virtual photons. Those photons take momentum from one particle and give it to another, causing the push and the pull that we see as a smooth electromagnetic force. Photons mediate electromagnetism. And we've talked about whether these virtual photons can be thought of as real before, but what is real is the fact that the EM field is extremely well described as being made up of quantized chunks. If we use basically the same process to quantize slightly more complicated fields, we get other quantum forces and their mediating particles, the gluons of the strong force and the W and Z bosons for the weak. It should not be taken lightly that this stuff works so incredibly well. We take a classical field, make some symmetry arguments to guess what other fields might exist, apply quantization rules, and boom, we figure out almost all of the particles and forces that make up our universe. The standard model of particle physics is arguably the most successful theory in physics and perhaps in science. It's not surprising that we'd want to envelop gravity and space-time into the explanatory magnificence of quantum field theory. So, how do we proceed? Well, we need to identify the field that we are trying to quantize and then apply the quantization rules just like we did with the other forces and fields. We do know that gravity behaves like electromagnetism in some important ways. It has a strength at all points in space. It also supports waves, gravitational waves, that also travel at the speed of light. There are differences, however. According to general relativity, the gravitational field is not a field on top of space-time like electromagnetism, but rather, in a very real sense, it is the fabric of space-time. This tangling of what the field is and what it lives in is going to be a problem, as we'll see. But for now, let's proceed. Let's get a little more precise. In the Einstein field equations, the field we're interested in is encapsulated in something called the metric tensor, a 10-valued object made up of scalars and vectors with the value of every point in space. It's a field, albeit a very complicated one. Now, where the EM field can be thought of as a thing living on top of the background grid of spacetime, this tensor field of GR, in a real sense, is the grid of spacetime. In electromagnetism, the field changes with respect to the grid. In general relativity, the grid itself changes. This is going to prove to be complicated. But nonetheless, the grid, this spacetime, this tensor field is the thing that we need to quantize, so let's do that. We'll start with an approach that hopefully won't break anything. We're going to treat the gravitational field as a small fluctuation, a perturbation, to an imaginary flat and static background. We poke the flat spacetime very lightly and see what comes out, hopefully a graviton. This is a very standard approach in physics. It's called perturbation theory. Rather than completely changing our model, we just make a tiny adjustment to what we already understand and we see what happens. The result is usually a good approximation to reality, assuming the perturbation is very small. Take, for example, electromagnetism. We can understand the quantum behavior of this field by taking account of the exchange of different nudges to the electromagnetic field as represented by the exchange of virtual photons in different ways. For a weak electromagnetic interaction, only the most obvious exchanges matter, like the exchange of a single virtual photon. Stronger interactions require us to account for more complex exchanges, but it all works out beautifully and gives us the incredibly powerful quantum electrodynamics. When we do this to the gravitational field, everything is also fine. Not only can we do a sort of gentle quantization of a weak gravitational field, we get a glimpse of the quantum of that field, the quantum that mediates the gravitational force. The graviton, well, what does it look like? Well, it inherits all of its properties in a pretty non-negotiable way from the field it comes from. It's a massless spin 2 boson. Massless means it travels at the speed of light. Spin 2 just means it has a 180-degree rotational symmetry that reflects a sort of stretch-squish action on space, just like the gravitational waves that should be made from these gravitons. And boson just means you can stack infinite gravitons together to make, for example, gravitational waves. And just as virtual photons make up the quantum EM field, we can build the fabric of spacetime out of virtual gravitons. Cool. In a sense, we just succeeded in quantizing gravity. This approach of perturbative quantum gravity actually kind of works. We can use it to recover classical gravity, and we can even use it to make predictions, like Stephen Hawking's prediction of Hawking radiation, leaky black holes. So why don't we just stitch this type of quantum gravity to the rest of quantum field theory and say we have a theory of everything? Why not just add the graviton to the standard model library and move on with our lives? Not so fast. We need our final theory to explain the whole universe, but our perturbative quantum gravity only works in the case of very weak gravity. It doesn't work for places with extreme spacetime curvature like the centers of black holes. We also want to actually verify our quantum gravity theory with experiment, and our perturbative theory only works in situations where it's essentially impossible to differentiate it from regular Einsteinian gravity, at least with a human buildable experiment. We really need a full theory. So to finish the job of quantizing gravity, we have to see if we can generalize this to a theory that works everywhere, including where gravity is extreme. Now, as gravity gets stronger, our perturbations get bigger, and the corrections we need to make to our classical theory get larger. More technically, we need higher order corrections represented by more complex interactions via virtual gravitons. So remember how we do this for quantum electromagnetic interactions. We calculate the quantum EM force by summing over the possible virtual interactions that could have potentially occurred. For weak EM fields, it's enough to include only the most probable of such interactions, and that means the simplest ones, like the exchange of a virtual photon or two. For stronger EM fields, more complex interactions become important. That includes so-called self-energy terms, which result from the feedback between the different fields. These higher order terms involve loops that appear in the many Feynman diagrams that we sum together to compute a strong interaction. In a previous episode, we talked about the connection between these loops and the measured mass of the electron, and how they appear to make that mass infinite. But these sorts of infinities can't be real, or we wouldn't have a universe. So in regular quantum field theory, we have a way to remove them. It's called renormalization. It lets us sort of divide out the infinities by grounding them in measured values, for example by measuring the true mass of the electron. This is possible with regular quantum fields because the perturbative expansion, the sum of Feynman diagrams, only generates a finite number of infinities. That means it's still possible to absorb these into a finite number of additional terms added to our equation. Even if absorbing infinities sounds a bit hokey, it works incredibly well by grounding our otherwise infinite predictions in a few finite measurements of the real universe. Quantum field theory is able to make stunningly precise predictions of many, many things. Not a bad trade-off. Depicting the EM field as being made of virtual photons is successful, and that forces us to take seriously this picture of a quantized EM field. At some level, we believe that the EM field and the other quantum forces are mediated by particles. If we can do the same thing for gravity that we did for electromagnetism, then we can make the same argument for the reality of the graviton. So, we're ramping up the strength of our quantum gravity, increasing the complexity of our perturbative expansion, and hoping we can renormalize any infinities to get a sensible theory. And this is where everything goes catastrophically wrong. The problem is that gravitons interact gravitationally. They interact with themselves. The photon, on the other hand, does not interact electromagnetically, at least not directly. It interacts with, say, the electron field, which feeds back on the EM field. That extra step limits the complexity of the photon self-interaction and limits the number of self-energy loops, making renormalization possible. But a graviton can directly spawn other virtual gravitons, which can spawn more virtual gravitons ad infinitum. Instead of a finite number of self-energy loops, we get an infinite number of terms in our perturbative approximation that can't be renormalized or cancelled out with a finite number of real measurements. In cases of strong gravity, our quantum gravity theory becomes meaningless. We say that perturbative quantum gravity is non-renormalizable. We can also think about this in terms of the strength of the gravitational couple. Stronger as the field gets stronger, ultimately sending the field's strength to infinity. So This straightforward approach of quantizing gravity leads to nonsense. Maybe then it follows that we can't build the gravitational field out of gravitons after all. And does that mean that the graviton doesn't exist? Well, not really. What it means is that this simple picture of quantum gravity that we get by applying the same quantization methods as the other forces isn't right. There may be a theory of quantum gravity that just can't be got by the simple perturbative approach. Interestingly though, the graviton itself that we found by that method that apparently doesn't work may lead us to the final answer. So even though the perturbative approach didn't get us all the way, that picture of the graviton is almost certainly right. If the graviton exists at all, then it has to be a massless spin-2 boson. Nothing else can generate the Einstein field equations in the classical limit. And that's why when we find a theory that predicts a massless spin-2 boson, our ears prick up and we wonder if we found a potential for quantum gravity. And that's exactly what happened with string theory. This was originally meant to be a theory for quark interactions, but a graviton-like particle popped out of the math in such a profound way that it sparked a many-decade quest to find a stringy theory of everything. You can't avoid the graviton in string theory, and in string theory you also avoid the rampant infinities, because at the smallest scales where gravity can be the strongest, the graviton field itself is smeared out over the vibrating strings at the theory's core. Now, there are other approaches to quantum gravity like loop quantum gravity and others. All of them have a graviton because without a graviton there's no path to classical gravity. It's again sounding like the graviton is inevitable, but again, no. It's only inevitable if gravity is fundamentally quantum in the first place. If the final theory looks more like quantum mechanics than general relativity, then we need a graviton. But what's the alternative? Well, it's that the fabric of spacetime doesn't have discrete chunks. It's not made of gravitons. Maybe a smooth, continuous spacetime is fundamental in some way. Now, a number of theories favour this option. Even Roger Penrose is a proponent, encouraging us to gravitize the quantum rather than quantizing gravity. Fit quantum mechanics into general relativity rather than the other way around. Ultimately, though, finding evidence of the actual existence of the graviton will be critical to confirming the quantum nature of gravity and even which quantum gravity our universe has. Now, as I hinted, that's going to be really hard to do directly. We'd need to build a solar system-sized particle accelerator. Fortunately, there are brilliant methods to observe the indirect effects of the interactions of a quantum graviton that we can do right now. For example, spotting the mediation of quantum entanglement by a gravitational field or a Cavendish experiment, but with exceptionally tiny masses. One of these methods may pan out very soon, or we may have to start astro-engineering our mega collider. Nature has set a last gigantic hurdle to understanding her deepest laws. We need to understand and then to find the graviton, and then we'll hold the building blocks of space-time. Thank you to Brilliant for supporting PBS. Brilliant is where you learn by doing, with thousands of interactive lessons in physics, math, programming, and AI. Brilliant helps you build your critical thinking skills through problem solving, not memorizing. Each lesson starts by helping you master the foundations, then levels you up to increasingly challenging problems. And if you're into physics, Brilliant offers a calculus course designed to help you understand how physics works. In the calculus course, you'll begin with rates of change, explore derivatives, and work your way up to three-dimensional geometry. To try everything Brilliant has to offer, go to brilliant.org/spacetime or click the link in the description. Brilliant's also given our viewers 20% off an annual premium subscription, which gives you unlimited daily access to everything on Brilliant.
empire were gathered, the rape of the colonies was all poured in there and so on and so forth. But I think Karl Marx was quite right in studying in the British Museum. He was right in using the resources and, in fact, the liberal values of the civilization that he was trying to overcome against it. And I think the same applies in
both scarcity. Trust me, I have been reminded. But yeah, I think the video really resonated with people because it actually does try to imagine an alternative way of setting up society. In this case, it's a society where reputation is the currency and not money. The one issue here, though, is that this vision is based on the premise that we get this technology that leads to a post-scarcity society. In the Orville, they created a little something called a matter synthesizer, basically a Star Trek replicator that makes anything people ask for, and it's a technology that allows them to create this post-capitalist world of abundance. In that video, I talk about the dangers of relying on a single technology like this to save us without our society being ready for it. But one thing that I didn't touch on so much is the fact that we already have the technology and social infrastructure in place to actually provide a decent life for everyone on this planet right now. For example, we produce more than enough food for 10 billion people, and yet millions starve. We have cheap renewable energy, yet our society still relies on fossil fuels. Have you ever thought about how much money, like specifically the size of the check it would take to solve the climate crisis? Probably not, right? But scientists, well, they've actually estimated a number for this. And it's totally doable, and that very thought is liberating. The number is around 2% of global GDP to avoid a rise in global average temperature of more than 2 degrees Celsius by 2050. And that's completely reasonable. That's less than the 2.4% of global GDP we spent on the military in 2023. Even though an actual utopia may not be around the corner, a dramatically better world, a sustainable, more egalitarian society is actually within our technical grasp. So the real issue here is actually with our institutions and the way we distribute our resources. And yes, with our imaginations that seem to lag behind. Now, I'd love to see more entertainment that actually imagines a different way of organizing ourselves, a different future. So to avoid being a total hypocrite myself, I've dedicated the rest of this video to a very specific idea that offers such an alternative based on what we have and not some miracle technology. Jason Hickel is one of my favorite academics because he doesn't try to obscure his ideas in overly complicated, hard to understand language, but instead lays out the problem of our time at hand and then offers a very concrete path out of them. To be a little more specific, Hickel is a champion of something called degrowth. You might have heard this term before. It's become a lot more popular in recent years, especially since COVID. Now, Hickel wouldn't call degrowth a movement, but more like a specific way to think about the future of a society where we, the people, decide what our resources are spent on. Some would call it a socialist policy, which unfortunately has a lot of negative connotation these days. But now a lot of people hear degrowth and they think it's a movement to halt progress in our society, to stop growing completely. But that's actually not true. Degrowth is basically a solution to two of the most pressing issues of our time. One being our crisis of well-being, and two, our deteriorating environment. And it's a direct rebuttal to the religion of our time that perpetual economic growth equals progress in our society. So it's an answer to the fact that we cannot save our environment or civilization through the economic growth paradigm. It's simply not feasible, exactly because growth is based on profit, and profit inherently relies on short-term planning. So first, to have any sort of meaningful conversation about this, we need to define what growth actually means. And here I'll let Jason speak for himself.
Growth defined by economists, which is what we're talking about here, is a very specific thing, which is an increase in total aggregate production in an economy as measured by market prices. Let's get this very clear. It's not about social progress. It's not about innovation. It's not about good things necessarily, et cetera, et cetera. And so according to this metric, £1 billion worth of tear gas is valued exactly the same as £1 billion worth of healthcare or affordable housing or something like that.
It's hard when you think about it, right? But this is the problem we have in a capitalist society, that we have this specific metric we call growth that we let decide what to produce. So here, the question we need to ask is really about who controls our production system, or the means of production as it's sometimes called. Like very literally what we use our resources for. Hickel argues that our current production system doesn't value social progress or human flourishing, and certainly not environmental repair. For example, it doesn't value things like universal healthcare, education, public transportation, renewable energy, affordable housing, and even meaningful work, which are all foundations of a good life that don't require us to hustle for most of our waking hours so we can pay rent or see the doctor. No, instead, our production system values profit. And that's the bottom line. That's capitalism. And when we think about the idea of capitalist realism here, the idea that we can't imagine an alternative to capitalism, then it's easy to see how our current production system has become super normalized in our society too. But if we look at some examples, it becomes very obvious why this is a completely absurd state of affairs. Take renewable energy. As it stands today, over 90% of global renewable power projects are cheaper than fossil fuels, and they've been cheaper for many years. Right now, solar power costs 41% less than the cheapest fossil fuel option. But we still rely on fossil fuels for our energy demands because, and this is the crazy part, even though oil and gas is more expensive, it's still more profitable. A big part of the reason for this, as the energy economist Nick Butler puts it, is that there's just less competition in fossil fuels. The barriers to entry to the renewables business are much lower than in oil and gas, and that increases competition and lessens profitability. Think about it. Renewables are cheaper and save the planet. Fossil fuels are more expensive and destroy the planet. I think I speak for all of us, at least us the people and not the ultra-rich, when I say that no one wants this, because it's destroying our planet and creating massive inequality. So to frame it differently, our growth-oriented system is actually a fundamentally undemocratic system.
Now, this may seem strange to hear for those of us who live in democratic political systems, where we get to elect our officials from time to time, right? Even if we acknowledge that these democratic processes are inadequate and corrupt. But when it comes to the economic system, right, the system of production, which shapes our civilization, determines the direction of our future, and is what we are engaged in most of the time in our waking hours, right? Not even a pretense of democracy is allowed to exist. Production is controlled overwhelmingly by capital under capitalism, and that is specifically the major financial firms, the commercial banks, the big corporations, and the 1% who own the majority of investable assets. So these people who control finance and productive capacity get to determine how to use our labor, how to use our planet's resources and our planet's energy, what to produce, and then who benefits from the yields of production. So we don't get a say over what gets produced, for what purposes, who benefits, and what to do with the surplus. Highly undemocratic, okay?
Now, what's especially absurd about our commitment to economic growth, the thing that capitalist realism has instilled as the normal way of organizing, right, is that it relies on the false notion that we have unlimited resources. But of course, we don't. And the limited resources that we do have are being extracted in a way that is destroying our environment. Perpetual economic growth is quite literally not feasible for the future of humanity. And that's also why, green growth movements like a Green New Deal, for example, doesn't really make sense.
It's absurd on so many different levels, let's put it that way. It's a very common discourse, and of course it seems to make sense, right? I mean, we start from the premise that growth is necessary for the economy, and everyone assumes that growth is automatically good. I mean, the discourse is basically growth is innovation, improvement, social progress, et cetera, et cetera. But this is not at all what growth actually is. I think it's quite important to point out.
No. Like he said before, for growth, $1 billion of produced tear gas is the same as $1 billion invested in healthcare. And that's the real point of this video. It's about the discourse. Because we think of capitalism as the only real option, right? It's hard not to internalize that sentiment and think that degrowth and socialism in general won't work. But in reality, it's endless growth that's pushing us towards the literal end of the world. It's precisely that apocalyptic scenario we seem to be able to imagine much more easily than any new economic system. WALL-E shows us the end of the world. It doesn't show us a system where we decide what our resources are used for. A few individuals save humanity, right? And the movie doesn't even show us what that new world looks like. There's something that I've been thinking about a lot recently that Jason Hickel also talks about. So, in most political democracies in the world, like the US, like Denmark, the UK, and so forth, there's a Green Party that advocates for degrowth-like policies. Now, I think it's interesting and also empowering to think about what would actually happen if we all, or at least, half the population, if we decided to vote for them.
Yeah, so if the Green Party takes power, then we've effectively had a socialist revolution, isn't it? and this is the point I want to make, is that the things that degrowth calls for cannot happen within capitalism.
And to be fair, I know it sounds super unrealistic that everyone suddenly votes for the Green Party, but fortunately the option is there for us in our liberal political democracies. Just like there's an option for me to make this video because of free speech, right? It's possible. Just like investing 2% of global GDP to save the planet is also possible. And so I think we need to internalize that these possibilities are real and they're attainable. This is also what political movements are built on. Because if we don't imagine a better future, then we certainly won't get one. And I would encourage everyone watching this to start imagining a different way of organizing ourselves on a large scale, so that it becomes easier for all of us to internalize that these possibilities really are real and attainable. I recommend Less is More by Jason Hickel, and also if you're interested in more specific local ways of degrowth and how it might work, check out Slow Down by Kohei Saito. I genuinely also love to hear your thoughts on all of this in the comments, and if you think that movies like WALL-E and YouTube commentators in general actually do make a difference. If you want to support the videos I make, you can do that on my Patreon page. I also post some updates there and have audio versions of my videos too, and it really goes such a long way. Also, a huge thanks to Flaky for being a sponsor, and thanks to all of the supporters there as well. And I want to give a big thanks to cinematographer Ben Engrave for helping me with the opening shot of this video. Looks super dope. And a big thanks to Raul and Anais too. And don't forget to check out my friends at Planet Wild. If you'd like to see them in action, you can watch their mission, turning power lines into insect highways, right here.
This video is brought to you by Brilliant. Click the link in the description to take advantage of a special offer for Arvin Ash viewers. You've seen this 1,000 times. Magnets pulling things, even with very large weights. It almost seems magical that this invisible force can be so powerful. Why do magnets attract? What is the mechanism? What's actually happening behind the scenes at the atomic and quantum level? We're going to keep asking why questions until we get to the ultimate answer. And that answer is way more fascinating than you might think, and it's probably something you've never seen before. That's coming up right now. You've probably learned in school that magnets have a north pole and a south pole, and opposite poles attract while like poles repel. But that's really just basic. It doesn't tell us anything. To truly understand magnetism, we need to zoom all the way in, down to the atomic level. Magnets are made of atoms, and atoms are composed of a positively charged nucleus surrounded by negatively charged electrons. These electrons are tiny charged particles that orbit the nucleus, kind of like planets orbiting a star. Well, not exactly, but we'll get into that later. For now, let's just visualize electrons orbiting the nucleus like planets around the sun for simplicity. The animation you see here is a decent mathematical approximation. Each electron doesn't just orbit randomly. Electrons have a quantum property called spin. Spin is not easy to visualize because it is a quantum property. It's not exactly like a spinning top, but it is a type of intrinsic angular momentum that particles possess, even though they don't physically rotate. It's intrinsic, meaning it's a property that electrons have, similar to the way they have a negative charge. Each spinning electron generates its own miniature magnetic field. The magnetic field lines represent the strength and direction of the force another magnetic material would feel in the vicinity of the magnet. Now, most materials have electrons spinning randomly in all sorts of directions, so their magnetic fields cancel each other out, resulting in no overall magnetism. But in certain materials like iron, cobalt, or nickel, something special happens. In these special materials, electrons tend to align their spins with each other due to quantum mechanical interactions. I'll explain what those interactions are in a minute. When electrons align their spins in this synchronized way, their tiny magnetic fields combine, becoming stronger and stronger. Large groups of aligned electrons create microscopic regions called magnetic domains, where all electron spins point in the same direction, creating a strong local magnetic field. Initially, these domains themselves are randomly oriented, canceling each other out at large scales, so the material overall is not magnetic. But when you magnetize a piece of iron by exposing it to another magnet or electric current, you force most of these domains to align in the same direction, turning the material now into a magnet. So that's how we create a magnet. Okay, but we still haven't answered the big question. Why exactly do magnets attract each other? The standard classical explanation, which you've probably heard before, is this. Magnets interact through their magnetic fields. These fields are like invisible patterns or lines coming out of the North Pole and going into the South Pole. You can even see these patterns if you sprinkle iron filings around a magnet. The filings line up neatly along these invisible field lines. When opposite poles of two magnets get close together, their field lines naturally flow from one magnet to another, creating a continuous loop, a stable, lower energy state. Nature loves lower energy, so this configuration pulls the magnets together. Conversely, when two like poles face each other, their field lines clash. They don't flow smoothly into each other, but push against one another, creating tension or pressure that drives them apart. This is the standard explanation you'll get in high school and some college courses. But since you're watching my channel, I know that like me, you would find that explanation highly lacking. What's really going on at the quantum level? So let's go real deep right now. First, what exactly are these field lines? At the deepest level, magnetism is explained through quantum electrodynamics, or QED. QED is the theory that describes the electromagnetic force, which is one of the four fundamental forces of nature. It is perhaps the most well-understood theory in quantum mechanics. I have a couple of videos on this. I'll leave a link in the description if you want to know the history of QED.
We're going to go to the Proxmox website. We're going to go to the Proxmox website and download, at the time of this writing, the Proxmox VE 7.3 ISO installer. We're going to burn that to a bootable image on a bootable flash drive. Now, for pfSense.
As a society, we've become used to computer problems of one kind or another, just as we've become used to computers. We're so used to them, in fact, that few of us stop to think of the extent to which they now play a role in our everyday lives, a role that shows every sign of growing even bigger.
If you look at sort of the process of the technological revolution that we're all in, it's a process of taking very centralized things and making them very democratic, if you will, very individualized, making them affordable by individuals for a small collection of tasks, if you will, sort of from the passenger train to the Volkswagen.
I mean, you think back just a couple hundred years and people could barely even travel between states, let alone get information from one place to another instantaneously. That is power. That is so powerful, having instantaneous information transfer. That's the biggest breakthrough of all of it.
Back in the day, you used to have to know how to code or at least how to speak a programming language to interact with the computer. Nowadays, all you have to do is swipe right. So the purpose of this video is to lay a good foundation to step by step understand really what's going on inside a computer. And I mean, like, physically, we're going to demystify at least the major functions that happen and how it interacts with what we call software. We will eventually be making specific references to HVAC equipment, but none of what we're talking about is specific to only that industry. So if you're not in that field, this should still be a good watch. Imagine you have a light bulb in a circuit with two switches in series. We know that in order for the light bulb to light up, we need to complete the circuit so the current can flow through it. So that means that in this case, we need to close this switch and this switch. We can make a little table so that we can map out what will happen in different situations. With both switches off, the light doesn't shine. With switch A on but B off, it still doesn't shine. The same goes for when A is off and B is on. Then finally, with both switches on, the light does shine. Now what if instead we connect the two switches in parallel? Now, in order for the light bulb to software. We will eventually be making specific references to HVAC equipment, but none of what we're talking about.
Making them affordable by individuals for a small collection of tasks, if you will, sort of from the passenger train to the Volkswagen.
I mean, you think back just a couple hundred years and people could barely even travel between states, let alone get information from one place to another instantaneously. That is power. That is so powerful, having instantaneous information transfer. That's the biggest breakthrough of all of it.
Back in the day, you used to have to know how to code or at least how to speak a programming language to interact with the computer. Nowadays, all you have to do is swipe right. So the purpose of this video is to lay a good foundation to step by step understand really what's going on inside a computer. And I mean, like, physically, we're going to demystify at least the major functions that happen and how it interacts with what we call software. We will eventually be making specific references to HVAC equipment, but none of what we're talking about is specific to only that industry. So if you're not in that field, this should still be a good watch. Imagine you have a light bulb in a circuit with two switches in series. We know that in order for the light bulb to light up, we need to complete the circuit so the current can flow through it. So that means that in this case, we need to close this switch and this switch. We can make a little table so that we can map out what will happen in different situations. With both switches off, the light doesn't shine. With switch A on but B off, it still doesn't shine. The same goes for when A is off and B is on. Then finally, with both switches on, the light does shine. Now what if instead we connect the two switches in parallel? Now the circuit from the light to the battery will be complete when we close either switch A or switch B, right? And if we close both, not much changes and the light keeps shining. The same kind of table can be made for this arrangement, defining what will happen in each scenario. And we call this a truth table. There's no gray area here. We can logically map out the output, or whether the light shines, given a specific input, the position of the switches.
Logic refers to the process where you outline what the outcome should be given a particular set of inputs. And think about inputs as just different scenarios that can come up. So I can tell you, if this happens and this happens, then what should be the result?
So how do we go from this very basic manual logic to something like a computer? Well, what if instead of having to flip switches by hand, we replace these manual switches with relays? Now we can use an electric signal to drive the relays open or close or off and on. And you can see that this matches our first scenario, where in order for the light to turn on, both relays had to be on. You can still think of pressing these buttons as a way for me to change the inputs and thus get different outputs. But instead of a person pressing these buttons, they could just be electric signals coming from somewhere else. Ultimately, if you look at what's going on in the wires going to the coils in the relays, there's either 5 volts when I push the button or 0 volts when I don't. And those are two different conditions or signals. When I push the button, or even when I don't push the button, I'm providing the system with a little bit of information or data. This is literally the smallest amount of data we consider in computing terms. And it's so small that we actually call it that. We call it a bit. Again, there's only two options, on or off, also referred to as high or low, or in this case, 5 volts or 0 volts. To simplify all this with computers, we arbitrarily refer to the two states as 1 or 0. So you can think of this circuit as a type of gate that only allows signals to be passed through when certain conditions are met. And for this reason, this is called a logic gate. Specifically, this is an AND gate. And here's a symbol and truth table for it. We also covered OR gates, where either A or B input being a 1 results in an output of 1. Logic gates are the building blocks for all traditional modern computers. And we'll soon see why. But even back in the 40s, when the first real computers were being developed, designers chose a different component to build logic gates, the vacuum tube. Vacuum tubes work on a similar overall principle as relays, as we can have one circuit that controls another circuit. But how it does it is completely different. This glass vacuum enclosure houses two metal strips called electrodes. One of the electrodes is heated by a filament. When voltage is applied across these electrodes, electrons sort of boil off and jump off the heated electrode in a process called thermionic emission. Since the other electrode is positively charged, the electrons are happy to cross the gap and flow across the circuit. In this configuration, the vacuum tube acts as a diode, since electrons can only flow in this one direction. But we can add one more electrode called a grid to control the flow. And the way we do this is by changing how positively or negatively charged the grid is. If it's negatively charged or negatively biased, then the electrons leaving the heated cathode will sort of hit a roadblock. Remember, like charges repel and opposites attract. Enough negative charge in the grid stops all current flow in the primary circuit. On the flip side, when the grid is positively charged even just a little bit, the electrons leaving the cathode don't really mind and they keep traveling across the gap, re-establishing current flow. How they thought of this, I have no idea, but it's super clever, and to get some hands-on experience, I built this little circuit. This is called an inverter, as it takes one bit of information and flips it to be the opposite. That's why when I push the button, the light turns off. Here's the truth table for it, and honestly it's as simple as it gets. What I realized though is that even just making this simple circuit with this vacuum tube, I found it very hard to work with for a few reasons. So the question is, why then did they overwhelmingly choose to use these over relays in the 40s, 50s, and 60s? To answer this, I hooked up the vacuum tube to an oscilloscope, mapping the control signal to the grid compared to the flow across the primary circuit. And you can see that the signals follow each other really closely. If I zoom in, there's essentially no lag. Each one of these squares represent 1 microsecond. The vacuum tube responds extremely quickly. Now, when I take the same measurement across just one of these relays, it initially looks the same. It's a fairly quick response. But when I zoom in, you can see a big difference. There's a big lag here between the time I pass the control signal to close a relay to when the primary circuit actually closes. It's something like 10 milliseconds. So comparing the two, the vacuum tube is many times faster than a relay, because it has no moving parts like the relay does. For this reason, the otherwise inconvenient vacuum tube took over, resulting in some truly massive computers that took up entire rooms or buildings and consumed an enormous amount of electricity to perform just a few calculations. And really, the problem was that we were reaching the limit of how big we could build them. The operating principle of the vacuum tube worked just fine, but we needed something more practical. Enter the transistor.
It was the invention of transistors that basically have allowed us to achieve the computing power that we have so far, because of the fact that we're able to introduce these components that used to be very large. Now we can miniaturize those components to be able to build smaller circuitry with very tiny transistors embedded in them.
At the heart of any transistor is silicon, an atom which has 4 valence electrons. When these atoms come together, the electrons like to pair up and create a tightly knit structure. Because everything is so neat and organized, the electrons are sort of locked down, and this material acts as an insulator. If we try to pass current through it, it just won't work, as there's nowhere for the electrons to flow. They're happy staying in their structure. But some really smart people figured out that we can change this property by simply mixing silicon with other elements in a process called doping. So the first element is phosphorus. Phosphorus has 5 valence electrons. So when we mix a few of these atoms into the silicon structure, they'll fit right in, but they'll have an extra free electron which is somewhat able to move and wander around. Now, if we apply a charge to this phosphorus-doped silicon structure, the free electrons will be attracted to the positive side of the battery, making room for more free electrons to come from the battery, and we get current flow through the material. We refer to this specific material as N-type silicon. The second element is boron, which has 3 valence electrons. Much like phosphorus, this atom has no problem taking its place in the structure, but this time instead of having an extra electron, we have the opposite, what we consider an electron hole, or a place where electrons could and would like to flow into. This material, called p-type silicon, will also conduct electricity, since now we have a place for electrons to flow and fill in from nearby atoms, creating more electron holes in a chain reaction. With these two materials, what we really care about are the free electrons and the electron holes. These two are considered charge carriers that allow charges to flow through each material. And things really get interesting when you put these two materials together. Immediately what happens is some of the free electrons will jump over and fill in some electron holes here, meaning those charge carriers are gone basically. Now this middle area becomes kind of like an insulating barrier because it's completely depleted from any charge carriers. Now when we apply a voltage differential across both materials, the result depends on which direction we apply the charge. If the negative side of the battery is connected to the N side, then a bunch of the electrons will flow into this material, making it negatively charged. At the same time, electrons will leave the P side to go into the battery, making that P side positively charged. This so-called bipolar junction creates a big imbalance, and if the battery voltage is high enough, eventually the electrons from the N side will be so attracted to the P side that they will start jumping across this barrier, wanting to fill in the electron holes. This creates a constant flow in this direction. So what happens then if we flip the battery in the opposite direction? Well, some free electrons from the N-type material rush to the battery's positive side, and some electrons from the negative battery terminal enter the P material to fill in some electron holes. And that's it. There'll be no flow across the junction. This is exactly how a diode works, using an N and P junction to only allow current to flow in one direction. And from here, we just have to add one more chunk of N material to make a transistor. So this is our control circuit. And this is the primary circuit that will be controlled. When the control circuit is on, electrons are already flowing across this junction, right? So when there's a voltage across the primary circuit, some of these electrons that have already crossed this junction are close enough to this positively charged region to jump this other junction and establish a flow through the transistor. If we make this middle P region even smaller, then most of the electrons will choose to go this way. So now it only takes a little bit of current to control the transistor. And as soon as we stop the flow across the control circuit, the primary circuit will also stop flowing because there's no way for the electrons to be able to cross these two junctions without help. We call the middle of a transistor the base. And confusingly enough, due to the long established idea of conventional flow, which is opposite to electron flow, we call this side the emitter and this side the collector. Here's a schematic for an AND gate made out of transistors. We can consider the two bases of the transistor are input bits. And this LED light indicates if the output is on or off. In order for the current to flow, we need to turn on both of these transistors by providing a voltage to their base. The nice thing is we can actually build this circuit to look nearly identical to the schematic and test it out. When I power the first transistor at the base, nothing happens. But as soon as I power the second one, the light turns on, meaning our output is now a 1 or on. But as nice as it is that this circuit looks just like the schematic, it's much more practical to model this on a prototyping breadboard. So here's the same thing on breadboard. But I have added 2 buttons, one for each input, and these blue LED lights indicate when I'm pressing the button. We can make any logic gate out of transistors. Here's an OR gate, for example. Imagine just how big of a breakthrough transistors were when first introduced. Just to make this simple logic gate, their size and power consumption was much smaller compared to vacuum tubes, while still retaining their lightning speed.
So at this point, you might be wondering, how are these logic gates useful? I don't really get it. And to be honest, that's how I was. But now that we've made it all the way to the transistor, I can finally show you how we can put these logic gates together to perform useful operations like, say, adding two numbers.
We all know how to add numbers, right? We use the decimal system to add, say, 12 plus 9. Since 2 plus 9 is 11, we take the 1 and the remaining 1 carries over to the next row, which combined with the other 1 gives us 2 and we get 21. So we're all used to this decimal or base 10 system, but in order to be efficient, computers have to use a different system, the binary system. This system uses the number 2 as its base, raised to some power. So for example, 2 to the power of 0 is 1, 2 to the power of 1 is 2, 2 squared is 4, 2 cubed is 8, and so on. Every number gets twice as large as we keep increasing the exponent. The great thing about binary is we can represent any possible number by combining these powers of 2 together. So if we just want the number 4, we can point to this position here and that's it. But if we wanted 6, we combine the 4 and the 2, 4 plus 2, and we get 6. Or a bigger number like 13, we combine 8, 4, and 1, and we get 13. So how do we express 13 then with this system? Well, with computers we just make a distinction between the powers that we want to use versus the powers that we don't use. And to do this we use a string of 1s and 0s. 1s showing the spots we do want to use, kind of turning these numbers on and away, and 0s basically omitting these numbers or turning them off. So to represent 13, we need a 1 in the first position, a 0 in the second, a 1 in the third, a 1 in the fourth, and a 0 on the fifth. Each one of these positions is a bit, since it carries one bit of information, be it a 1 or a 0. And each of these bits is operated by a transistor. A 1 is represented when voltage passes through the transistor, and a 0 when it does not. So now we're expressing 13 as a 5-bit number, using 5 positions, so to speak. Technically, we only need 4 bits to express this number, as this 0 here is not really helping us. But it's not uncommon to have this happen. We could even express 13 as an 8-bit number, or even higher, and we just have more zeros. More bits just allow us to express higher and higher numbers, so yeah, they may seem like a waste when representing smaller numbers. For practice, let's look at 4-bit strings, and strings is just a name for these bits in a row. We can count all the way up to 15 using 4 bits. Expressed in binary, here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. Binary is definitely kind of weird at first, but then you start to realize how efficient it is. After all, we only need 4 little bits of information driven by 4 transistors to express up to 16 numbers in this case, including the number 0. Don't forget, 0 is one of the options. So now that we understand how numbers are expressed, let's go back to our original example and add 12 plus 9 using binary. To express 12, we combine the 8 and the 4, giving us the 4-bit binary string 1100. And here's the number 9. We combine 8 and 1, giving us 1001. We can add these together by putting them on top of each other, just like we did with normal addition. So here 0 plus 1 equals 1. 0 plus 0 is 0. 1 plus 0 is 1. And here, 1 plus 1 is, of course we know it's 2, but there's no such thing as 2 in binary, so you can think of this as getting 10 on your base 10 addition. You have to carry over one spot, and you get this. This is the number 21, and notice we had to use 5 positions or 5 bits, because with 4 bits we could only count to 15. So we did this all manually to show the process, but now the question is, how do we design a computer that can compute this for us? Let's take a look at this first operation, adding 2 bits from the same row together. We already showed how this works, so we can make a truth table showing all the possible combinations. 0 plus 0 is 0, 1 plus 0 is 1, 0 plus 1 is 1, and finally 1 plus 1 is 0. So if you remember, this truth table looks very similar to an OR gate. But this last situation is a little different. We want the output to be 0 when both our inputs are 1. And this actually constitutes what's called an exclusive OR gate, or XOR gate, our third major type of logic gate. There are different ways of making an XOR gate, and this example uses 5 transistors. You can see that it starts out with the same layout as an OR gate, but all this extra circuitry is designed to restrict the path to ground coming out of this OR gate when both A and B inputs are on. And so our truth table matches exactly what we needed to do to add 2 bits together. Of course, I've gone ahead and assembled this circuit, and you can see that when either input is on, the output is also on. But when both inputs are on, the output turns off. So we are in essence adding 2 bits together. The problem with this setup though is that it doesn't account for our remainder. Like when I add 1 plus 1 together, the output is 0, but we should have a way of knowing that there's an extra bit that should carry over to the next bit column. And with that in mind, we can add some more circuits like an AND gate to indicate that the sum has resulted in a carry bit, shown here as this yellow LED light. Now, I want to make a circuit that can add 2 4-bit numbers together, like when we added 12 and 9. And to do this, I would need a bunch of logic gates. It actually gets a little more complicated when you're spanning across multiple bits, and I did the math. I would need 64 transistors to make the logic gates for this circuit. We could do that, but it'd honestly be kind of a pain, so instead we can use these little guys called integrated circuits, or ICs. Integrated circuits can house all kinds of things in a smaller platform. For example, this one contains 4 different AND gates within it. Or this one here has 4 different OR gates. So this allows us to minimize the number of components and wiring for all kinds of circuits. I just need 5 of these chips to make the 4-bit adder circuit. And still, it takes quite a bit of wiring to connect this all together. To be honest, I made a few mistakes building this, so there was lots of troubleshooting involved. I also had some silly issues with some wires just not making good enough contact with the breadboard, which was a bit of a headache, but in the end, I finally got it to work and I felt this was definitely deserving of 2 thumbs up. I'm using these dip switches to input our 2 separate 4-bit numbers into this adder. So here I have 1 plus 1 equals 2. Then 3 plus 3, which equals 6. Or like in our example, I can input 12 plus 9. 12 is again 1100, so I set the switches that way. Then 9 is 1001. And after I get that input, we can see that the result is 10101, which is correct, that's 21. I think this is a good demonstration of how we go from transistors to logic gates to something useful. Imagine having to make this with vacuum tubes. 64 vacuum tubes to add some little numbers. We've definitely come a long way, but this is still a behemoth of a device and it's still not super useful. I mean, who wants to be inputting binary and reading the results as LED lights? So that leads us to the next step. How do we go beyond just logic and make these devices work for us? One of the key aspects of any computer is its ability to easily communicate useful information. Our little 4-bit adder is not very good at this. But take a look at this, the world's first calculator. It could display the results using these nice numerical displays. These are called Nixie tubes, and personally I think they're really neat. We've got 10 digits, 0 through 9, all formed in wire like a filament kind of. But unlike a light bulb filament, it's not the filament itself that glows, but the neon gas right next to it due to some crazy science of the electrons flowing from the filament to this mesh. So to make these work, we just have to apply voltage from the mesh to one of the digit filaments. Each one has a different pin at the bottom. Unfortunately, these take a lot of voltage, like 85 volts DC just to turn on. My DC power supply doesn't even go that high, so I use this variable transformer and the bridge rectifier we made in the last video to get higher voltage DC. If you haven't seen that video, I've attached the link in the description. With this much power, you'd have to use a bunch of relays just to drive the digits, which I mocked up so you can see it in action. Mine only counts up to 5, but you get the idea. As interesting and mechanical as all this is, it takes up a lot of room and consumes a lot of energy, which seems to be the trend associated with older technology. So the next best thing for this kind of application are segmented displays, like this LED one. These are much lower power, and connecting power through each pin results in each of the 7 segments to light up. We can use an integrated circuit like this one that will sort of translate a 4-bit signal to light up the individual segments and build the correct digit. Here's the translation chart with the 4-bit input marked as a string of L's and H's for low and high. And here are the outputs for each segment of the display. What kind of blew my mind is that they're achieving all this using logic gates and some pretty complex wiring. This is not really an easy conversion from a 4-bit input to a 7-bit output. And there are techniques to figure out what kind of logic gates and circuits you need given specific inputs and outputs using what's called Boolean logic, which is kind of like logic algebra, and these things called Carnot maps, which allow you to visualize sort of what you need. Now, as displays get more complex, there are better ways to achieve these kinds of conversions than just using straight logic, like for example in this LCD display. This display is receiving information from this Arduino board, but everything that's going into the display is fed by these 4 wires. Let's take a look at the signals for the letters A, B, C, D. For the letter A, we get this cable transmitting a high voltage while the rest remain at 0 volts. In binary, this is the string 0001. We can use this conversion or lookup table provided by the manufacturer to see what that means. So 0001 puts us in this row. And for the letter A, we need to be in this column, which is 0100. Honestly, I can't quite see this signal in the scope, and I suspect it's just too quick, but that information is there somewhere. Just for fun, if you woke up this morning wondering what the 4-bit signal for captive air looks like, here you go, this is for you. What this display is doing is much more advanced than the 7-segment display. First off, we're taking what's really an 8-bit input signal made up of 2 4-bit chunks. Each 4-bit chunk can be arranged into 16 possible combinations, and 16 by 16 means we have up to 256 possible combinations in total. Then we have to translate each combination into a symbol comprised of 40 dots. Each dot then has to turn on or off to create a complete visual representation of each character or symbol. Doing this using nothing but straight logic would be crazy, so instead, this display uses memory.
I remember every fact I'm exposed to, sir.
Commander, what is the capacity of your memory?
800 quadrillion bits.
Memory comes in 2 general flavors, long-term and short-term. I don't know how data's memory works, but this display uses long-term memory embedded or programmed at the factory to translate the 8-bit signals into the correct output. The signal we provide to the display is nothing more than an address used to point toward the data for each one of these 40 pixels. The data for each address is permanently stored as a 40-bit string. So how do we do this? How do we store data permanently? There are actually quite a few ways, but the most common for these applications involves the use of a special transistor called a floating gate MOSFET. Let me just give you the basics. This transistor allows for current to flow or not flow, just like with our transistor from earlier, and this is controlled by this circuit here. In this normal condition, if we apply a low voltage across both circuits, the electrons flow. We can read this flow, resulting in a logic high or 1. However, when we provide higher voltages across the terminals, we can cause electrons to become trapped here in the floating gate, potentially forever. Now when we try to flow electricity across a transistor at a normal voltage, the electrons stuck in the floating gate reduce or even prevent the flow across the transistor. We can again read this flow and determine it's now too low, resulting in a logic 0. If we wanted to reset the transistor, we could apply specifically high voltages across both circuits, attracting and releasing these electrons back into the body. So in essence, by controlling the presence of electrons in this layer, we can allow the transistor to flow or block this flow permanently or until we decide to change this. Memory that uses these floating gates is called flash memory, like this little SD card that can hold 128 gigabytes of flash memory. Just for reference, there are 8 billion bits in a gigabyte, which means in this little SD card we can store over 40 billion of the characters we've been talking about. And how we do it we'll get to in a second. But first, let's look at the other type of memory, short-term memory. Let's say you're adding these 4 numbers. Maybe the computer can only handle adding 2 numbers at a time, right? Like with our adder. So it will add these 2, Then it will remember this number, load it, add it to the next, then remember that number, load it, add it to the next, and so on and so forth. We could, in theory, hold these numbers in long-term memory, but that would be painfully slow. With flash memory, it can take a few milliseconds to access and read or write data, which in computing terms is quite an eternity. But with short-term memory, it's a nearly instantaneous process. So let's see how it works. So far, we've only been talking about logic gates in a linear fashion. But interesting things happen when you feed the output of a logic gate back into its input. Take this OR gate at the most basic level. If we wrap its output back to one of its inputs and provide a 1 to its other input, its output will stay as a 1 even after I let go of that other input. And it will stay like this until I disconnect all power to it. We can take this concept further to build something like this data latch. Say we have 1 bit of data coming in, turning on and off and just kind of doing its thing. But what if I want to save that data now, capturing that 1 bit of information in its current state? I can hit this button to enable the mechanism to capture that slice in time, and there you go. Now we've captured, or in computing terms, latched this as a 1. Maybe then the data keeps coming and going, but the latch still remembers what it was at the time that we told it to remember. But now I want it to remember again, when the input is 0 because I'm not pressing the button. You can see now that it does remember. It stored that moment in time as a 0. So this data latch uses logic gates to store data as either a 0 or a 1. And 1 bit might not be so useful, but we can scale this up. For example, we can put 8 of these together in a row, making what's called a data register that stores 8 bits, which is also the definition of 1 byte. This is one way to do it, but generally the best way to scale memory up is to use a grid configuration like this. Then in order to access a specific bit, we need much less wiring. But how do we access each bit individually? Well, we use addresses again to pinpoint where the data is in the X and Y axis. And when voltage is applied across these two wires, we can use an AND gate to access this specific memory latch and only that latch. This way of packaging memory into a grid is how we're able to condense so much memory into such small spaces like the SD card.
Now that we understand basic logic operations and how to store and access memory, we can start getting into the job of a microprocessor, which is basically like the brains of a computer.
When we're talking about a microprocessor or microcontroller, it's a device that has several different components. So it has certain memory components where it stores data, and it also has processing units such as adders that allow the microprocessor to perform arithmetic operations. So when a programmer is writing a computer program, the different components within the microcontroller are the ones responsible for executing those instructions. So we discussed a very simple component, which is a half adder, but from that component you can create adders for multiple digits. Any type of arithmetic operation can be derived from those very simple components. So that's how a microprocessor does the legwork of processing. We have all these billions of transistors that are used to build the logic gates, such as the AND gate that we discussed, and then the logic goes from very high level mathematical components into lower level recursive actions of using these components to make the calculations that it needs in order to execute any given program.
Thankfully, when we program computers to perform certain tasks, we're not just writing ones and zeros. Here's a program written by a person in the language called C. This program is designed to print or display on screen even numbers that exist from 1 to 50. First, we tell the computer that we only want to look at whole numbers represented by this I. Then we tell it to look at numbers less than or equal to 50. Finally, we tell it to take those numbers, and if after dividing them by 2, the remainder equals 0, meaning it was an even number to begin with, then we go ahead and print that number on the screen. And that's it. Of course, without prior knowledge of coding, this looks like gibberish, but what's it like for programmers?
Generally, I tell people, well, a computer program is not that different from human language in the sense that there's a structure that you are expected to follow. There are ways in which you refer to different things, so things have names, or in the case of a computer program, there are certain addresses that you refer to. So it's a very structured and methodical way to manipulate data. It's not as flexible as human language in the sense that you can't be vague about what you want to do. You have to specifically use the predefined structure of the language in order to achieve what you're trying to do.
Now that we've written this code in C, there are a couple of translations that need to happen in order for it to be ready for the microprocessor. First, a computer program translates or compiles the C code into what's called assembly language. This is now a very specific set of step-by-step instructions for each portion of the code, designed to work with specific processors. For example, load this value to this specific memory register, or compare two values, then depending on what happens, maybe jump to this location on the code, then keep going, and so on.
Yeah, it's basically a set of instructions that are allowed. Each processor has, however many dozens or hundreds of instructions that it's allowed to do, and then operators for all of those. And it's essentially another language. You can write all your code in assembly if you wanted to. In fact, we had to do that in college to get an understanding of how it all worked. But no one really does that. That's just like for learning.
The final step before feeding these instructions to the microprocessor is to translate them again, this time finally into just ones and zeros. This process links each step to the appropriate binary string that will direct the processor to execute that instruction. For example, the term load register might be 1110. The register location might be 1010, and this value might be 0010. Now, there may be times when programmers do work directly with this low-level code. And looking at just ones and zeros, it's really easy to get confused and make mistakes. So a common translation from binary is hexadecimal or hex. Hex breaks down any binary string into 4-bit chunks. We know that each 4-bit chunk can be represented in decimal as a number from 0 to 15. But hex is even simpler than that in that it only uses one character per 4-bit chunk. So once we get to what would be 10, we start instead using letters. For example, here's a 16-bit binary string converted to hex. This is much easier to read. And we can do the same thing to our machine code. But this is just for people. When feeding the code to the computer, ultimately it's going in as binary because transistors just want to know if they should be on or off. And that's what the processor wants. Basic specific instructions.
So when you're trying to understand how a computer works and someone explains to you what logic gates are and what they do, you start thinking, well, a lot of these operations are very basic, right? Like anyone can add two binary digits together. But whenever you start thinking about the computing capabilities that we have today, then you start realizing the complexity that these devices can handle just because of the fact that they are able to perform so many operations concurrently at any given time. Now, a lot of these operations are driven by a clock. So every time there's a clock tick, that tells the existing components that they need to perform an action. So you get a signal that says, okay, process the next bit, process the next bit, process the next byte.
You can make a simple clock circuit out of transistors, capacitors, and resistors. This one's pretty slow. You can also use an integrated circuit designed for this application, and in both scenarios, the speed of the clock depends on this resistor and capacitor combination. So we can speed up this clock easily, and the signal looks like this. But how fast can we go?
The frequency is very, very high, so you get millions and millions of operations every second. So when we're talking about 1 megahertz is 1 million operations per second, 1 million cycles per second. And we can keep going on. 1 gigahertz is 1 billion cycles per second. So the speed at which these transactions are occurring is extremely high. So that's how computers are able to process data and information so quickly that it's almost seamless from our perspective.
So for half a century now, the trick to making computer hardware better and better has been miniaturization, which allows for more transistors to fit into smaller packages, consuming less power while running at faster speeds. Moore's law predicts that every 2 years, the number of transistors on a microchip will double. We've actually been following that since the 70s, and the result is that today, this consumer desktop processor can perform about 400 billion operations per second. and yet it's smaller than one vacuum tube from the earliest computers. And with this, the real question becomes, what do we do with all this power?
So everything here is stuff I've worked on for Captive Air in some way, shape, or form. This right here was kind of my big project that I've had for basically the whole time I've been here. When I first joined the company, we didn't have our own circuit boards really. We were using, can't remember what it's called. It's a really annoying technology to use. And there's like this pre-built off-the-shelf thing that you have to program, and it's got these weird pins that you plug in. It's just a pain. And we really just wanted to replace all that and make it significantly cheaper and easier to customize and make it exactly how we want. A really big Captive Air thing is if you see something and it's not quite what you want, get rid of it and we'll do it ourselves and we'll do it better. And I love that mentality, and it seems like we always keep doing that, and it has never served us wrong. So this is the ECP103 board, which is for the hood ventilation control. We can have a kitchen hood, a very long kitchen hood that has multiple like cooking elements, and in this long hood you can have multiple exhaust fans and temperatures associated with each section of the hood. And say one side is just way hotter than the other, why would you want to turn the fan on over here when you're maybe not even cooking? So we can control the fans individually based on their temperature needs. So if it's super hot over here, we can have this fan going, you know, full speed, this fan maybe low speed just to help make up for some of it if it's drifting. And then temperature kicks up over here later, then we spin this one faster. So it's all individual control per what's needed where. That's just one example of the many things this board can handle. And I think one of the hardest parts about embedded software or embedded design is knowing what you can do and knowing what to do with it. Like I go home and I try to think of hobby projects to do with things like this, and it's not always easy. There's a lot of use cases for things like this, but they're not always practical. The hard part is making something that is useful, that people will actually need or want to buy. And that's something like this. You need something to control your hoods efficiently and properly. You can have an on-off switch, sure, but you're not gonna have safety features or energy efficiency or anything like that if you're just on-off switch. It's such a cool concept. And the same thing's happening for the MUA board and HVAC in general.
Whether it's hood packages, advanced refrigeration systems, makeup air units, or you name it, all these HVAC technologies benefit greatly from the use of smart controls. And one thing they all have in common is the fact that they interact with the real physical world. So let's look at some sensors commonly used in these applications. The simplest one I could find was this float switch. This is used to detect a certain level of water in something like a condensate drain pan. When water is present at a high enough level, the float moves up and it mechanically opens the switch. So the output of this sensor is really simple. It's just one bit. The circuit is either on or off depending on the water level. A computer would have no problem handling this signal just as it is. We can let the program know that when the circuit outputs a 1, there's no water, and when it outputs a 0, there's water. There are quite a few other sensors that have this same kind of binary output, even if internally their design is more complex. Here we have this pretty fancy sensor used to detect oil in the compressor. Regardless of the high-tech infrared technology this sensor uses, in the end, the output is either a 0 or a 1. That's it.
But what about something like temperature? I mean, we can't always just have a switch that's on and off. Oftentimes we want to know the actual temperature value in degrees Fahrenheit.
So here's a temperature sensor which uses a thermistor, which is just like a resistor whose resistance changes greatly with temperature. At room temperature, the resistance across this thermistor is around 10,000 ohms. But when I heat it up, the resistance goes way down. Now the trick is, how do we convert this resistance to a temperature value? In going into this, I thought, well, that's simple. You just have some sort of conversion chart to convert the resistance to a degrees value, and you're done, right? Sort of. In my reasoning, I skipped one major point. This analog signal that is resistance, the computer doesn't know how to read that, like, at all. Natural resistance in a thermistor is about as far away as you can get from ones and zeros. So what we need to do is convert the signal using an analog to digital converter, or ADC, into a binary string for the computer to read. There are a few ways to do this, but they all use a component called a comparator. This device compares two input voltages, and if this voltage is higher than this one, it outputs a logic 1. Otherwise, it outputs a 0. So the first thing we do is we apply a set steady voltage across the thermistor. Since the thermistor is changing resistance due to temperature, we know that the output voltage would also change with it. The higher the resistance, the lower the voltage. We can sample this voltage, let's say it was 3.4 volts, and feed it into the top leg of, say, 4 comparators. Okay, now let's say we knew that the range of voltage we're looking to measure is between 5 and 2 volts. And I'm just making this up. We can take 5 volts and apply it to this bottom reference leg of the first comparator. Then we can continue the circuit and add a resistor here, meaning this one's only getting 4 volts. Then add another resistor so this one only gets 3 volts, and another so this one gets 2, and then send this all to ground. Now each comparator is comparing our 3.4 volt input to a different voltage. So this top one would output a 0 because the reference is higher than the input voltage. Same with this one, but this comparator would output a 1. And so with this last one because 3.4 volts is higher than both of these reference voltages. So as the voltage from the thermistor loop changes, so does the binary output of this analog to digital converter. Now we finally have a binary number whose value we understand and can reference to a lookup table to convert to a temperature. Now, this ADC is very crude and not too precise. If, for example, the voltage coming in was 2.8 volts, all we would know is that it's between 2 and 3 volts. But we could scale this up and add more comparators to get more and more granular readings. The ADC used in this board is actually integrated into the microcontroller, and it's a 10-bit ADC, which means it can measure voltages in up to 1024 sort of little slices.
So you could have a lookup table with 1023 values for temperature corresponding to the resistance of the thermistor. But after talking to Alex, I realized that's not what we do, and the reason why we don't do that is that that would take up a lot of memory.
Instead, the processor is loaded with about 100 values, or 10%-ish. So if with some luck, the output of the ADC is one of the values that we do store, like the number 530, then we just take that temperature and we're done. But if the output of the ADC falls between two values, like if it's 520, what will happen is the processor will look at the two closest temperature values and perform some simple linear math to approximate the correct temperature. The nice thing is, the region we care most about precision, which is sort of 50 to 80 degrees, happens to also be the region in this thermistor's temperature curve in which the change in temperature compared to resistance is also the most linear. So that means that this approximation is most accurate in the area that we care about the most. And that's not a coincidence.
I am so proud of the software that I've written for this. It has been so fine-tuned, and it's just amazing how much we have fit on this tiny little chip. This tiny little chip only has 64 kilobytes of space total for code. And that's like nothing. That's like what NASA had when they went to the moon the first time. But the reason we chose something like this is because it's so easy, clean, and cheap. You have such full control and so little overhead that anything you want to happen, you know you're the one causing it to happen, for better or for worse.
So we use many input devices to gather data, but it's still important to be efficient. If you remember from our psychrometrics video, we can measure any 2 parameters of moist air to calculate any other property. So instead of directly measuring things like dew point, wet bulb temperature, or vapor pressure, we calculate these values using just temperature, relative humidity, and the corresponding equations. And this is extremely useful for units that refrigerate or temper the air.
So thus far, we've only really been talking about the local operation of these controllers, but there's a lot more we can do with them.
Something that we can do and that we generally do is connect these controllers to a building management system. In this case, we have a gateway, which we will call a SCADA up here, that's collecting data through the Modbus protocol, and that all happens through this cable. It's collecting all the data that this controller is using, and then it's sending it through a cellular connection to our servers and to basically a database that can be accessed by a website to interpret that information and display it in a meaningful manner so that engineers and end users can make decisions and monitor the operation of the system.
I want to talk about this Modbus protocol that Juan mentioned. You know, what is a protocol? What does that mean? And for this demonstration, I have this old dusty keyboard from like 2003.
The standard keyboard uses around 104 keys. So if we take apart this wire, you might expect to see 104 tiny individual wires. But that's not the case at all. There's only 4 wires, and in fact, only 2 of them carry data. That's because this keyboard is communicating through a protocol called Universal Serial Bus, or USB. If we actually look at the signals going to the computer, it's these really fast pulses that, in the end, just make zeros and ones to represent different keystrokes, sent out as little packets of information every fraction of a second. The USB protocol dictates how this information is packaged and communicated, and protocols are extremely useful in many applications like HVAC.
With analog signals, I can only get like temperature or any type of readings, but it won't tell me what that controller is trying to do. I can't tell anything about its logic. I can't tell anything about what its set points are. Now, if I have a network connection, the physical connection is obviously much more simple because of the fact that I don't need wires for every single type of signal that I'm trying to monitor. So it's much, much easier. And then I can not only get data about the sensor inputs to that controller, I can also get data about the decisions that that controller is making and why those decisions are actually happening. So I'm allowed to increase the level of complexity of that communication by having a protocol that dictates how that exchange occurs.
The Modbus protocol works based on a master and auxiliary system. In this scenario, the DCV board acts like the master, and it can control, in theory, an unlimited number of auxiliary devices like variable frequency drives. The devices only communicate when the master requests something, and the auxiliary devices are always listening for these commands and reacting to them accordingly. Since we can daisy chain several devices onto the same wiring, this exchange happens with only one auxiliary device at a time, which makes Modbus relatively slow.
There are faster protocols, of course, but Modbus has good benefits. You could run really long cable links. If you have something on the whole other side of the building, you can just run Ethernet cords, which is just so nice.
Since the Modbus protocol is a defined standard, we can translate it and repackage it into any other standard protocol using what are called gateways. These devices simply convert the signals from one protocol to another, which is useful if we want our Modbus devices to interact with other building management systems using a different protocol, like BACnet. We also have to repackage data for things like wireless communications. The board we use for this is called SCADA, which stands for
Supervisory Control and Data Acquisition. That's exactly what it does. It basically harvests data from all of our products and puts it all on one server for everybody to view. It's crazy how much you can see on CastLink. It's insane to me every time I go on there that you can just see so much in so many places all over. And they have control too. From CastLink, they can go press a button on there and turn fans on somewhere on the other side of the country.
There is no guarantee that the equipment will operate as it was intended to once you pass it on to the end user. If at some point settings are changed or something was not set up properly right after the building was turned over, then there's a risk that those units will potentially operate 24/7, operate at times where there's no one in the building. So a building management system takes away those risks. It gives you visibility of what your different components are doing and making sure that they are not only operating efficiently, but also operating only at the times that they need to be working. So it all comes down to energy and comfort in a lot of cases. Like you're able to look at the different sensor data, the different operational statistics of the equipment just to make sure that everything is working as intended at all times. you start becoming very, very intimately familiar with the equipment that you're monitoring. So you have all these data sets, all this data from equipment that's all over the world, experiencing all these different environmental conditions and serving this broad range of spaces. And you know how it's operating, you know how it's responding to different types of changes. So having all that information allows us to better model what a unit should be doing at any time. So we can take all that data and we can potentially implement machine learning algorithms to detect faults or any other type of situation before it actually creates a problem in a space, or we can create a model of a unit to try to perform reinforcement learning algorithms for future fine-tuning. It's going to become much easier and more practical for more applications to make use of machine learning and AI in order to implement solutions. You know, if you have a team of engineers that are constantly trying to optimize the operation of HVAC or any type of machine for that matter, the fact that we have all this data and the fact that we're able to interpret this data accurately and the fact that we have so much computing power to manipulate that data to will eventually allow us to just automate some of the actions that are taken and have our engineers focus on different types of things. So everything that's repetitive will eventually be phased out from those types of environments. And the activities that I'm leading within our teams internally are focused a lot on incorporating more of those types of algorithms into our day-to-day. So yeah, I think, you know, it's just very interesting, very exciting.
I read a survey in Scientific American in the early 70s, and what this survey had done was it measured the efficiency of locomotion for various species of things on the planet, birds, fish, dogs, and it ranked them. And man sort of came in with a rather unimpressive showing about a third of the way down the list. But someone at that magazine had the insight to test the efficiency of man riding a bicycle. And man riding a bicycle was twice as good as the condor, all the way off the end of the list. And it really illustrated man's ability as a tool maker to fashion a tool to amplify an inherent ability that he has. And that's really exactly what we feel we're doing. We're really sort of blazing the trails for the 21st century bicycle, but to amplify a slightly different inherent ability that man has, the ability of a certain part of intelligence. Right now we're at the mechanical part of intelligence, where one of these devices can free a person from many of the drudgeries of life and allow really humans to do what they do best, which is to work on the conceptual level, to work on the creative level.
Ever wondered what all those strange folders like bin, etc, and user actually do in Linux? In this video, we'll break down the Linux file system structure, starting from the root and exploring each top-level directory one by one. Whether you're a beginner or just curious, this will help you understand how Linux organizes everything behind the scenes. So let's get started. Everything in the Linux file system starts from a single point, the root directory, represented by a /. It's the top of the hierarchy, and every other folder branches out from it. To make sense of what's inside, we can group these top-level directories into 10 general categories. There are system binaries for core commands, boot and kernel-related directories that help the system start, configuration files that define how Linux behaves, user-related directories like personal home folders and root access, and shared libraries that support essential programs. We also have mount points and media used for external devices, system and runtime information that reflect what's happening in real time, multi-user resources for software and logs, temporary files used briefly by the system, and finally, folders for optional software installed separately. Now let's look at each of these in more detail, starting from the root and working our way down. In Linux, everything begins at the root directory, represented by a single /. It's the top-level folder from which all other files and directories descend. Think of it like the trunk of a tree. Unlike Windows, which uses separate drive letters, Linux has a single unified file system, and everything connects back to root, including external drives and partitions. You might also see /root, but don't confuse it with /. / is the starting point of the entire system, while /root is just a subdirectory. It's the personal home folder of the root user, who has full administrative access. In other words, / is the starting point of the file system, while /root is just one of the many folders inside it. This separation helps maintain a clean and secure system structure. Now let's move to one of the most important system directories, bin. This folder contains essential command line tools that are needed for the system to function properly, especially during boot or when running in recovery mode. Commands like ls, cp, mv, and cat are located here. Basic utilities that let users list files, copy data, move items, or view text. Unlike some other command directories, the tools in bin are always available, even if other parts of the file system haven't loaded yet. That's why bin is critical for both everyday use and troubleshooting. Regular users typically never need to modify this directory, and doing so could break core system functionality. It's best to leave bin untouched unless you know exactly what you're doing. Next is the sbin directory, which stands for System Binaries. While bin contains general-purpose commands used by all users, sbin holds specialized system utilities, mostly used by the system administrator or root user. These commands are critical for managing and maintaining the system, especially for tasks like mounting file systems, checking disks, or shutting down the system. Most of the tools in sbin require superuser privileges to run. So, unless you're an admin or troubleshooting low-level issues, you'll rarely need to touch this directory, and you definitely shouldn't modify it without knowing the risks. Next up is the lib, short for libraries. Just like apps need support files to run, many commands found in bin and sbin rely on shared libraries, similar to how programs on Windows need DLL files. These libraries provide common functionality like reading files or handling input and output, so individual commands don't have to include all that code themselves. Depending on your system, you might also see lib32 and lib64, which store 32 and 64-bit libraries respectively. You'll also find kernel modules here. These are small pieces of code that can be loaded into the Linux kernel on demand, kind of like plugins that extend its functionality. This directory is also not a place regular users should modify. Tampering with it can easily break basic commands or even prevent the system from booting properly. Now let's talk about USR. Despite what the name suggests, it doesn't store personal user files. It stands for Unix System Resources and contains most of the system's user space applications, libraries, and documentation. A typical user doesn't usually modify this directory directly, but it's where many installed programs live. You'll notice that USR mirrors several directories from the root level, like USR/bin, USR/lib, and USR/sbin. This structure exists because USR was meant to hold non-essential software that complements the essential tools in bin and lib, keeping the system organized and bootable even if only the root partition is available. Since this area is usually read-only and managed by the system, it's best not to modify it manually. Next, let's take a look at the boot directory. This folder contains all the files your system needs to boot up, like the Linux kernel, initial RAM disk, initrd or initramfs, and the grub bootloader files. One important file here is grub.cfg, which tells the system how to load the operating system. In some setups, especially in dual boot systems or when disk encryption is used, boot might even be placed on its own separate partition to ensure it stays accessible during startup. Since this directory is so vital, even small changes can render your system unbootable, so it's best to leave it untouched unless you're following specific instructions and know what you're doing. Let's move on to the dev directory. This folder doesn't hold regular files. Instead, it contains device files that act as interfaces to your hardware. In Linux, everything is treated like a file, even devices, and this is where they're exposed to the system. For example, dev/sda might represent your first hard drive. Whether it's your hard drive, USB stick, keyboard, or even virtual devices like dev/null, they all show up here. You'll find two main types: block devices, like hard drives, which handle data in chunks, and character devices, like keyboards, which handle data as a stream of characters. These files are managed dynamically. Linux adds or removes them as hardware changes. While it's interesting to look through, interacting with these files directly can affect your hardware, so be cautious. Next up is the etc directory. This is the central location for system-wide configuration files, covering everything from network settings and user accounts to startup scripts and service configurations. For example, etc/password holds basic user information, and etc/fs tab defines how drives are mounted at boot. Most of these are plaintext files, designed to be readable and editable by system administrators. The name etc originally stood for etc., but some like to think of it as editable text configuration. Either way, it's a vital part of system management. While it's worth exploring to understand how Linux works under the hood, changes here should always be made carefully, since they can affect how the entire system behaves. Next is the home directory, the personal space for regular users. Each user has their own subdirectory here, like home/Alex or home/Emma, where they store documents, downloads, projects, and personal settings. These folders keep user data separate from system files, making backups and account management much easier. User-specific configuration files often live here too. Many are hidden by default. Hidden files in Linux usually start with a dot, like .bashrc. You might also see a shared or public folder, depending on the system, used to exchange files between users. By default, users don't have access to each other's home folders unless permissions are changed, adding a layer of privacy. And unlike most system directories, home is meant to be customized. This is your space to create, modify, and save files freely. The root user, however, has a separate home directory located at root instead of inside home to keep it isolated and more secure. Next, we have media. This directory is where modern Linux systems automatically mount removable media like USB drives, CDs, and DVDs. Each device gets its own subfolder inside media, often named after the volume label. It's the place where users can access the actual contents, like photos, documents, or software. Unlike other mount points like MNT, which we'll look at in the next chapter, media is designed for removable devices and is often handled automatically by the system. Media is user-friendly and often doesn't require administrative privileges. Desktop environments like GNOME or KDE handle this seamlessly, so your flash drive just appears ready to use. To clarify, Dev holds the device files that represent the hardware itself, while media is where those devices are mounted and made usable by the system. So think of Dev as the raw connection and media as the convenient entry point for users. Let's move on to MNT, another directory used for mounting file systems. Traditionally, this is where system administrators would manually mount external storage, like USB drives, partitions, backup disks, or remote file systems, especially during system maintenance or recovery. Unlike media, which automatically mounts removable devices for user access, MNT is reserved for manual, temporary mounts and is typically used by the root user or advanced scripts. For example, if you need to access the contents of a failing hard drive or mount a network share during troubleshooting, MNT is the go-to location. It doesn't contain anything by default and only is content when something is actively mounted there. While you might not use it often as a regular user, understanding its role is helpful when working with Linux at a deeper level. Now let's take a look at proc, one of the more unusual directories in Linux. Like dev, proc is a virtual file system. It doesn't contain real files stored on disk, but instead provides a dynamic, in-memory view of the system. While dev represents hardware devices, proc acts as a live interface to the Linux kernel and running processes. Inside, you'll find folders named after process IDs, like proc/1234, with details about each process, as well as system information files like proc/CPU-info and proc/mam-info. Essentially, proc is a vital tool for monitoring, debugging, and interacting with the system's inner workings in real time. Next is sys, a virtual directory like proc, but with a different purpose. It's part of the sysfs pseudo file system and acts as a dynamic interface between the Linux kernel and your hardware. Here, the kernel exposes information about devices, drivers, and system buses. For example, you'll find folders representing CPUs, memory blocks, USB ports, and even the system's power state. What sets sys apart is that it's not just for reading information. Certain files here can actually be written to, allowing advanced users or system tools to tweak kernel settings on the fly. This makes sys a key backend for system utilities like udev, power managers, and hardware configuration tools. It's structured hierarchically, so each hardware component and subsystem has its own path. But unless you're developing drivers or customizing hardware behavior, you typically won't need to interact with it directly. Next up is run. This in-memory directory holds temporary runtime data used by the system and applications right after boot. It's created very early in the startup process, before most of the file system is ready, and everything inside it disappears on reboot. You'll find subdirectories like run/user for user sessions or run/lock for system locks. Unlike proc or sys, which expose kernel and hardware information, run is writable and is used by running processes to communicate, track state, or store short-lived files like process IDs and sockets. It replaced older directories like var/run and var/lock, helping unify runtime data in one central, reliable location. Next up is the SRV directory, short for service. This is where data for services provided